All right, let it go.
Yeah, so I don't know if you still have on your phones this Mentimeter question 5 and 6.
No, it just says that you have already responded to this question. It doesn't show up with the.
So now I open the second one, the question number 6.
Yep.
Receivers. Yeah, some words are coming up now.
Answer 5 or you're not supposed.
Yeah, there was quite a few answers, but we can. I'll go back to that. So I jump to this one. I don't share my screen now. I need to do like this. So water quality seems to dominate the response or your answers, and air quality and dust, and a lot of other things as well. That's.
What about community acceptance? So like PM.
Yeah, that's probably to sort of earn your license to operate. I think the community, if there is communities nearby, and if there is not, the environment itself. But, sorry, someone else.
But it's not only the community, but as a country, it's. So,
Yeah.
so I think cannot go as far as. That's only the community.
Yeah, so you mean both, or?
I'm saying acceptance can go beyond the community living next to the mine.
Yeah. So I guess the community, if there are communities nearby, are the ones more or less directly affected, and then the country as a whole can be like in Sweden, for example, uranium mining is not allowed. But government has decided we're not allowed to mine uranium. But we have nuclear power stations. Yeah, exactly. So I'll just, is there any more sort of comments on what we need to monitor? I don't see community here. I'll add that.
Yes, acceptance.
Acceptance.
That's community acceptance.
Yeah. Yeah. And the previous question, only 12 responses. I don't know if it's possible to add anything to it now.
You cannot
Go back.
But no, now it pops up.
Yeah.
Oh,
So you can add more if you want to, but contamination seems to be sort of the main word that defines an environmental failure, that we contaminate. Probably you can say the environment or the community or the country, different levels as well. So I will see if this can probably stay open for you, and then I stop share this screen. So I seem to. This is not mine. It's not mine. Keeps disappearing. There, this one. So to sort of summarize a little bit, what we need to monitor and where can sort of be generalized, that sort of we can monitor the source, what we have, the tailings that we have, processed water and so on, and then the pathway and the receptor will be sort of the final, the environment, the community or the river or side, what we need to monitor. So we need to sort of follow the whole pathway. And I've already mentioned that that this is probably a multidisciplinary field where we need more specialists and not just engineers. And I was asking around a bit before I did this presentation, and I met quite a bit of frustration with colleagues in Sweden. But I also got some input from both North America and Australia and a few more places. So in Sweden, there is very much focus on how do you get your permit, how do you get approval for your operations, and not really sort of considering the protection of the environment. And when it comes to water quality, we kind of the experience is that there is a lot of conservatism, and sometimes the threshold levels are much lower than what actually the level would be to see an effect in the environment. And there needs to be sort of some kind of reason in this. We don't want to pollute the environment, but also I think it's important that mining companies spend the money on things where you get value for the money, where the money makes the biggest change. And then also, if it's not always a negative impact, sometimes there can be a change to the river downstream that can maybe improve biodiversity and life. So it's not always negative, and we must understand what the effect will be and what consequences it has, and not just look at threshold levels for different metals. And this we have one mine in Sweden that had to close, and for tailings facilities in Sweden there is a 10-year permit period, and you need to apply for a new permit. And there is some companies are scared now that they will not be able to renew their permits, even though there is not really any effect on the environment that can be measured. And also that there is actually some improvements that have taken place after downstream the mining area. So this will be the last one. I've listed some challenges here, and the question would be. Sorry, this was not this. Don't go back. So if the question is if you have any more challenges, or if you see any more challenges than these. Or if there is challenges you experience from your own facilities or projects that you've been working on. Why is trying to share my screen now again? Oh, I need to change this one.
Literally.
Mining affects stability. So this is something, it's a hot topic in Sweden, that one. We don't have any lined facilities. And I think in many cases, dam stability or dam safety and environmental safety is sometimes contradictory. So you have to not maybe choose in between the two, but see from question to question which is the most important. And if we do have a dam failure, it doesn't really matter if we have a liner. The consequences are going to be much worse than seepage. I think I will stop there, and I will collect all these answers for the PDF presentation. What do you have the Teams on there now?
Thanks, Annika. That's one of the things you mentioned. Just reminded me of one site that I had pretty interesting involvement. Actually, Edgar knows it pretty well as well. It's a mine that the original operations caused quite a bit of environmental impact. And at the end of when the original owners decided to leave, the government negotiated a new operator to come, and the outgoing operator had to put in a certain amount of money to cover closure costs, and the new operator put in a similar amount. And so they had a fund of money, and the new operator could actually get credits for doing environmental improvements. And so over a period of five or so years, probably a bit more than that, they were able to introduce new procedures and actually remediate the past environmental impact by putting covers over systems using actually the operating processes rather than any particular closure. So they're able to improve the water situation, so that the local river that previously had no fish in it for about 10 kilometres, fish were able to come back, and they restored the environment. So in that case, it was a positive environmental improvement. So anyway, moving on to our next session, which is about tailings dam visual inspection. It's a pretty topic that I'm pretty keen on, and I've just got a panel here to help me. What I want to do is try and develop an ICOL bulletin to give us some better guideline. I'll tell you in a minute about what the current guidelines say, but I've got some esteemed people on the panel here. You've already met Manuel. We've also got Leandro over on the right or your left. Leandro is a geotechnical engineer with over 15 years of experience in tailings dams and water dams. And he's worked all over the world, as most of the people seem to have, and in lots of different types of dams. But I'm particularly interested in Leandro's background because I know a mine that he works at up in Papua New Guinea, and it's got some very challenging safety issues, I guess, and be interested in what they do for their visual monitoring. And then we've got Rowan, who's also got 15 years experience on the left, on your right. And interestingly, he's currently involved in Cadia mine in New South Wales, where there was a failure about 6 years ago. So it was interesting. I don't know whether Rowan was actually going to talk about it, but I can say that they had a pretty good surveillance system and people were doing daily inspections. But if you know anything about the Cadia failure, some cracks were noticed at about 9 o'clock one morning when guys were doing some work. Actually, I think they were downloading some piezometer readout data on, I think, something like that, and they noticed these cracks. And then they looked, oh shit, what's going on? They looked down the bottom of the dam and they saw some bulging as well. So there was the visual inspection or the visual indication of a failure. And by the time, or in 12 hours time, 9 o'clock, or before that actually, I think it was about 7 o'clock in the evening, the dam actually failed and a slump came down. And so it was really only detected a few hours before it actually failed. Those particular cracks that were found were on a bench, not the crest. And so, I'm not sure what the inspection parameters were that they used, but nobody had seen these cracks before. And then subsequently they got some satellite monitoring system that were able to go back at the data and from the INSAR, and they were able to supposedly detect that the movement of the failure started about 3 months before it failed. So, whether those cracks were actually there, visible or not, no one will ever know. But it's basically an interesting question as to how we should be doing our surveillance. So I just wanted to, hopefully this is not working.
You have to press and then if it works.
Press what?
Just down.
Down? Yeah.
Very cool. Again. Maybe to the side.
Okay. So, what we're talking about is tailings dam inspection, who, what, when. So I think we need guidance on what to do here. In tailings dams, the scale is often a lot bigger than a water dam. So a lot of the ideas from water dam surveillance might be difficult to achieve. We have some specific issues like tailings pipelines, spigot performance, beach shapes, like we've talked about before. So quite a few different parameters from a water dam, so more of them, if anything. And we're supposed to be doing these routine inspections to minimise risks. And this is what we have said in the ICOL Bulletin 194. We need to do inspections to minimise risk. The inspection requirements should be specified in the OMS manual. Should be by trained staff at a frequency commensurate with the complexity of the operation and the classification of the dam. And once again, it's up to the EOR to decide what it is. We need to, the items that need to be monitored should be designated by the EOR. So poor old EOR is really carrying the can for deciding what to do. And so my question is, what guidelines is the poor old EOR going to have? And really, there aren't very many. In ANCOL, we have these tailings guidelines, and we do a bit more specification about what's required. And what we say is that a routine inspection by the operational personnel should be for a high or extreme dam, should be daily or 3 times a week. So most mining companies do this. They have an inspection every shift, essentially. So every day someone does an inspection of the dam. But how extensive is their inspection, and is it really what Ancold thought it would be? If they have a intermediate, if there's a significant dam, it's twice weekly or once a week. And obviously then there's more high level or more detailed inspections by engineers at some other frequency, typically quarterly or annually. But I'm really worried, thinking about the operators' inspections, like the inspections that you do on a routine basis. In the CDA, they say that the frequency of inspection should be commensurate with the consequences of failure and the past performance, and they should be weekly or monthly, and engineering inspections carried out by professional engineers. So really not much guideline. And to me, the issue of scale is a very important thing. We've got the water dam might be 200 or 500 metres wide. It might have a couple of benches, but a tailings dam could be 2 kilometres or 5 kilometres, like in Cadia. If you looked at the total length of the crest on the 2 dams, it's 10 kilometres. And then on that dam, there's probably 5 or 6 benches as well. And then there's the toe. So if you wanted to inspect the crest, the toe, every bench, you're probably looking at 100 kilometres that someone, and if you think about what Ancold would be expecting, or Ancold maybe, that would be done by walking, not by driving. What can you see from a drive-by? What's the access to benches? What's the vegetation like? So, it becomes very, very difficult to imagine doing a walking visual inspection of a tailings dam to the level of you think may be necessary to find any problems like these cracks at Cadia, for example. So this is why I've had this session. We want to get a bit of audience participation and thinking about it, because I'd like to develop an ICOLD guideline on what, where, who, when, why, how. It's a pretty big question, and I think I'd like to get a bit of feedback on it from the panel. So I don't know if anyone bursting to say something. Maybe Manuel, you are you ready to go? There's some microphones here. I'm not sure how we turn them on, but no. Oh, there you go.
Yeah, thank you so much, David, for really setting the scene. And the ICO guidelines on the old tradition is exactly what you've mentioned. Other guidelines and the Swiss guidelines, for instance, have a very similar approach. I think the Norwegian ones as well. I could correct me if I'm wrong, but essentially frequency of inspections based on the consequence assessment and types of inspections. The routine ones, the ones you do for like a comprehensive surveillance report, the ones you do for a safety review, and special inspections after you've had an issue, a flood event, an earthquake event. So really based on the type of loading and consequence assessment of the dam, you have different types of inspections. And then who is responsible and should be doing the inspections, from the dam operator on site to the engineer of record or professional engineers that work for the dam owner, and then like consultants or external third-party people that are not involved in the daily operation of the dam. So that's really the scene when it comes to visual inspections. And as of what to look for, it really has to do with failure modes. So the ideal thing is for each one of those credible failure modes that have been identified, really say this could be the symptoms, or this could be like the issues we should be looking for in terms of essentially seepage, deformation, vegetation, in some cases, at the toe, and we're talking about trenches or drainage trenches at the toe, or water dams that are part of the water management. So what to look for. The ICO guidelines really say go to your failure modes and link the failure mechanisms to what to look for. And finally, the other component is how do you do the reporting, and how do you track down those visual inspections? And in that regard, checklists are very important. So that's one key recommendation. You have a checklist that is really associated with components. So you really have to navigate through the failure modes, but then components. We usually do failure modes from the components from mindset, but then you can have interactions. But in any case, that's a good way of structuring your visual inspections. If you have components and subcomponents, and apart from checklists, pictures from specific points that are done on a regular basis, and even videos, and I'm really trying to do like a sketch. If you could do some measurements, sometimes if there's seepage, the extent. If you see a crack, maybe you can measure the length, the opening. So basic measurements associated with what you see with the visual inspections, a detailed location, and also nowadays we even have from tablets, mobile phones, where you can have those checklists and even the option to take pictures and voice notes as you do the visual inspection. So we have some tools to help.
Yep.
The final thing would be the spatial component. If you need to do 10 kilometers of 50 kilometers of visual inspections, that's
Well, that's what I'm getting at. So maybe, Rowan, take Cadia as a good example. I mean, after the failure, how have you structured the surveillance plan, if you like, and how do you do it? Who does it, and how frequently?
Yeah, so across our two facilities, we've got 3 technicians who are on rotating rosters. So we've always got 3 on at any one time, and they're walking on average about 12 k's a day. So you do have to question how effective is their monitoring going to be. After they've walked 6-7 kilometres, are they really looking properly?
Yeah.
So you have to take into account the human factor. We have investigated using drones to replace humans in some situations, not all situations, but in areas where we know we don't have any major issues, we can cover that ground quickly with drones. You can't see it as well, but you can cover it more frequently if you want to. But yeah, it's really the human element. How do you manage that fatigue? How do you actually make sure their inspections are being done thoroughly?
So do the general operators on the site, other than those 3 technicians, have any inspection role at all?
Not really. We roll out education on what to look for, whether if they see cracking, who to report it to.
Yep.
But typically the only people who are actually on foot are either the instrumentation team or the inspection technician. So the operators aren't really going to see a whole lot from a moving truck.
Yeah. Okay.
Traveling 50 k's an hour.
So I guess if they're doing 12 kilometres a day, and it was 100 kilometres total, so roughly every 10 days they would have completed a full inspection of the dam. Do they kind of map it in any way?
Yeah, between the 3 of them, we're hitting every bench once a week.
Okay.
So every section of dam is inspected once a week.
Right. Okay. that seems pretty good to me.
It's a Herculean task.
Yeah.
And there's definitely room for improvement.
Okay.
And we're going to just manage to get that in place to get a shortage of personnel.
Yep.
Plus we've got onboarding, bringing new people up to speed, the different training programs they have to go through to actually be effective. And then you have that historical knowledge. You always try to use the same people to do the inspections, but when you bring new people in, they don't know that history. So it's also having that record that they can go back and if they see something, they can go back and check it. Has this been noted before? Is it new?
Yeah.
Pre-existing.
Okay. All right. So, Leandro, in your experience, and particularly I'm thinking of the mine up in the highlands of Papua New Guinea, which is like a pretty high earthquake place and high rainfalls. Would you just explain a little bit about what the process is up there?
Yeah, sure thing. Before I go through this point, Dave, I think it's very interesting if you discuss a little bit about the different players that you have on the design, right?
Yeah.
Because based on different understanding you have from the design, from the embankment for the TSF. So we have regulators, we have independent review, we have ITRB, we have designer, that's we have a site representative that's follow the construction and with the KYQC role. We have all these people that have different levels of understanding of the embankment. And when these people go through to the site visits or to carry out with the visual inspections, they tend to look at the different things, right? For Hidden Valley, for example, as you mentioned, we are in a high rainfall place. That's it's more than 3,000 millimeters per year. In a very active seismic area that have seismic at least a week. That's we have a very good control. Tomorrow I'm gonna show a little bit more about this about this how you can make these controls. But these inspections has been taking place every single day by our site representative engineers and for the operators as well, on a weekly basis. And every single time that you have a special event, that's let's say 50 millimeters in 24 hours of rainfall. So we carry out one inspection to see what happens, what could happen. The same for the seismic events. So we carry out these visual inspections after these events. We always look at the instrumentation that we have in place to see if there is any abnormal measures on that space. We have annual inspections that's carried out for the design team. So that's the way that we are conducting these inspections in Hidden Valley.
Okay. So I guess I was thinking of those two mines you're talking about are probably lucky that they've got some engineering people. Some other mines might not have an engineer who's there every day, in which case the operators themselves have to do some inspections. So I've been involved in trying to train or succeeding in training operators so they can understand a bit more about dam safety, because most people who are on the dam sites are pretty smart characters. But often got qualifications of some sort, technical tradesmen or skilled people. So they really enjoy being trained, and they enjoy learning about what they're doing and how important it is. And so I guess in that case, it's a matter of how much inspection work those people should do, and how they do it. Anyone got any feedback, or you want to say?
One other comment I want to make was, especially at Acadia, where we're dealing with dams that are. Sure, I can say this. Yep.
He's looking at Eddie, who's the designer.
You have to consider the risk that you are putting these people in by having them inspect the dams on such a regular basis, and that can actually impact your consequence category population risk calculation. So you have to, it can be quite complex if we wanted to inspect the dams every day. So that's going to be a quite a large increase in exposure. So you have to consider that. But certain sections of the dam you just can't go. So like the Ram Slump.
Yeah.
So you have to consider other options that don't put people at risk.
Yeah. Okay. You mentioned the forms, Manuel, and like there is a few sort of standard ideas about what a form is. One of the best ones I ever saw was done by BMA coal in the coal mining fields in Queensland, and they had almost like a tarp built in. They had the inspection that might have been the pipeline or whatever, and every inspection that was on the checklist had a photograph of what was to be inspected, and then a little bit of a tarp about what's good and what's bad. And in cases where there was a like seepage flow or something, they'd actually have some numbers. If not that, it'd just be no cracks was green and cracks was orange or something. And I thought that was really good. Have you seen many different inspection forms?
Yes. So I think the inspection forms can be very simple, just with some basic questions. All the ones I've dealt with are really broken down into components. So you're going to have the crest. You have to tailor the form. So if you have several walls, you're going to have the crest for all those walls. If there's any structural condition or design that makes something different, then you want to have a specific one for that. And you include like parameters or symptoms or signs, very specific to that. Like, is there any water being accumulated? So is the drainage okay? Of course, cracks, and it goes on. If there's a crack, how long is it? What's the opening of the crack? When you have seepage, you can say, is it really outlined the extent of that seepage at a particular date? Can it be measured, or is it just wet, a wet area that cannot be monitored? Is it just dripping, or actually you have some flow that could be channeled and then measured? So all of those little details, even the type of vegetation that you can have in some area, you have different types of plants, and you can really ask for that in the toe of the dam. Do you see the stack of vegetation or not? Are all the areas accessible? Another good thing about the forms is including the option to add pictures. Now with tablets and the software, it's really good because all those forms can be transferred into the tablet, and as you're doing the inspection, you can take the pictures, and it's a very easy way to track it down. But then also, if you include in the form like a plan or a plan view, cross sections of that really helps the operator to even make notes and note down anything that they've seen or on site. And going back to the training and my personal experience with training, and I'm thinking now of really dam operators. So people who are not engineers, is that you can really go from very basic training that I think it should always begin with a failure rules, really telling them this can go wrong this way, and showing examples of past failures. That's really eye-opening for the dam operators, because maybe you find people who have been doing that for decades, but they were not fully aware of the other mechanisms. And you can even take it from there. So, and with some dam owners where the training has been going on even for years. The great thing is that you can really get down to the O&M manuals.
Yeah.
So you actually, in the training section, you use with the dam operators to really enhance and retouch and make those forms better and really to what they see. And there's a lot of feedback that you can get out of that. Plus the TARP's emergency action plan. So if you can do like an actual exercise with the dam operators of what would happen if you saw, let's make a guessing game, and you do that exercise of, okay, there's a crack, and then we have seepage, and it's increasing in 2-3 hours. So that is very powerful. And the good thing is once you have some dam operators trained, that knowledge can be passed on as more people. So that training should be, so visual inspections should really go hand in hand with that training.
Well, I think that's a very good point. And having operators involved in the OMS, I mean, so often you go to a site and the OMS has been, this is the Operation Maintenance and Surveillance Manual that I'm talking about, like that should be the Bible for how you operate the dam. Quite often it's written by their consultant with no input at all from anybody from site, and it might be okay, but they haven't got any ownership of that document, and so they don't even look at it, and it's just pointless. It's really meant to be developed by the people who use it. So I don't want to spend too much time because we've tried to catch up a bit of time, but Leandro, is there any training at Hidden Valley that you do for the operators?
I think this is a good point that you mentioned about the OMS first, because in our case it's opposite. The ownership of the document is the operator.
Yep.
And we just have, as a designer, we just have a section on that report to determine in terms of maintenance what you expect, in terms of threshold levels what we expect, and to determine which instruments we expect to have on the embankment. And over there, most of the personnel from the operator side are engineers. We just have a few technicians. And we are working with along with them to try to get them to speed to understand the principles of the OMS, the principles of the failure modes. So as I mentioned before, so we have the different levels of understanding about the design and the weakness of the design. So we're trying to get them to understand or get across the message to understand what's the weakest points of the facility. What's the most sensitive points that we need to look after during some certain times of events.
Okay, well, thanks very much. Well, that'll probably be enough to get people thinking about the issues, and we can thank the panel very much for your input. Yeah, well, while we do that, are there any questions? Sorry, I should have asked. Sit down again. Any questions or actually comments, experience that some people have had on their own sites? How you do it at your site? Yep.
Thanks, Benjamin, for Congo Democratic. Please, for monitoring of dam, it is better to do everyday inspection or day by day, 1 week by month, or just by month, one. Thanks.
The frequency of inspections really depends on the consequence assessment. So the potential hazard has a potential in the dam has. So if there's potential loss of life, how much? So in that regard, in the case of RDC, I'm not sure if you have some guidance, but definitely within the Nile Basin, there's some dam safety guidelines. And actually, there's an update of the dam safety guidelines for the Nile Basin countries, which RDC is part of. So that's a good starting point, where you have some guidance of the consequence classification for a dam. So based on that, then you really have the frequency of the inspections. So how often the routine inspections should be carried out, and by who. I'm really talking about the routine inspections, which it can really go from daily inspections to weekly inspections, even to a fortnight or every 2 weeks, or so twice a month or monthly, by month. It really depends on that, and then you can resort to different guidelines to really know exactly how often, the frequency of those inspections. But that's for the routine inspection. So if you have the comprehensive surveillance report, that should have a different visual inspection of its own. And if you do the dam safety review, which should be done, it's usually done every 5 years, which is, let's suppose we were designing the dam nowadays, what would we look for? And you could do like an overall review of the safety. And in some countries, like for instance in Australia and in New South Wales, you also have to do the risk assessment. So you actually have to, on a regular basis, revisit all those failure modes. And that really closes the circle. Because if you have the failure modes, you really know what to look for, what to inspect, and what to be looking for. And then with the consequence assessment, you know how often you have to do that. And so that you should be in a really good position from accounting for all those items. And you should be safe. And you can always use that as well to say, look, I was doing my homework if something goes wrong.
Yeah, that's another good point. I was going to mention that when we think about those inspection forms we fill out, they are actually legal documents. And if something does go wrong, people are going to come in to find out why. Someone's going to be trying to blame people. And so to have those documents filed away clearly that you've done the inspections properly, just like ticking all the boxes, but you know that they are legal documents and very important.
Yeah, I think just one more comment. I think sometimes you need to reduce the frequency of the inspections when you have some unusual thing happening on your embankment. Let's say that you have some seepage, inspected seepage. So maybe you need to reduce the frequency of your inspections. Maybe you have some piezometers that have some spike. So we need to reduce the frequency of your visual inspection as well. So I think we have a guidelines that can predict or can say how might be the frequency of the inspections. But I think that's as a designer, as you are, we need to have the sensibility to understand that how we need to reduce the frequency of the visual inspections. Decrease, reduce the frequency.
I'll reduce the frequency.
Reduce the frequency of the visual inspections. Let's say the guidelines say that you can do, we should do once a week. But if you have some issue, we can reduce this to twice a week.
Increase the number by reducing.
Yeah. Sorry, yes, you're right. Yes, increase the frequency. Yes, thank you. You got me. You got me. Thank you.
Yeah. Sorry, you're next.
Sorry, my name is Oliver from DFC. I want to jump a little bit on this topic because you are talking about the EOR. It seems like to get EOR to the site is kind of difficult. I mean, especially in Africa. So is there kind of corporation of EOR? How many companies are out there doing that job? Yes.
I think that really depends on In this case, it can be, again, we can look at the legal framework or the guidelines or the regulations and what they say and what they state. So depending on the jurisdiction, you may have some legal framework that says the engineer of record needs to have this qualification, this experience, or maybe there's nothing like that. And then it's really the dam owner who responsibly should just set the standard and ask for what the needs are. And the other thing is, how often should the EOR go on site? I think every facility is different, but with tailings dams, the construction is just going on forever. Maybe you finish a stage and you wait some time, but then you resume the activity. So you should always have someone working for the EOR, or can be the eyes and the hands of the EOR, and the EOR as well should be visiting the doing regular visits and being on site on a regular basis. Absolutely. But again, it's on the dam owner. Otherwise, you could always resort to the guidelines. So there's some pretty good guidelines. And if you don't have them, I'm thinking for RDC, you can definitely at least go for the Nile Basin framework. And so these safety guidelines, I can share them with you. They've been updated very recently in 2024. I was honored to be one of the reviewers of those dam safety guidelines for the Nile Basin countries, which RDC is also a member. And then we can resort to the excellent guidelines we have. Like the ones that they mentioned, the UNCOLD, CDA, and those are really good references.
Well, I suppose I'm really suggesting that they're probably not as good as they should be, and there's room for improvement. So
starting,
yeah,
at least it is a starting.
So I think we would like under our ICOLD committee L to try and think of some better start to develop some better guidelines. So we might. There was one question here. Sorry.
Yes. So whether there is any written guideline how to decide the number of equipments in the tailing dam, like piezometer or inclinometer, how to decide the number of?
You mean? Well, yeah, do you mean the number of instruments or? So, and thank you so much for the question, because it's a question that comes up like all the time, and all the trainings I've been involved in on dam surveillance, that's a question that always comes up. So what's the minimum number of instruments that we should have, and what type of instruments? And really the answer is potential failure modes analysis, PFMA. There's no rule of thumb. There's no general recommendation. It should really be driven by the potential failure modes for that very specific dam and foundation for that facility. So the materials that have been used, what we have in the foundation, the way it's been built, with what machinery, what technology, the deposition, in the case of tailings dams, and for water dams, all of that, the history. Each dam is like a human being with a different history and different DNA, and a very specific failure course. We have the generic ones, the generic mechanisms, but then if you have something in the foundation, that's going to be a different failure in that section, that area of the facility. If you have maybe one conduit, a decant tower going through the foundation, that's a different failure mechanism. So you really want to inspect, and the monitoring system should be really targeting don't spare the notes and have it purposely.
But if I can just butt in a minute, we really don't want to get off the topic because we haven't got much time. And I think the whole purpose of this course over the next 2 days hopefully might answer that question. So by the end of tomorrow, we've had presenters on different types of instrumentation and you might get a much better idea. And then going through our exercise, we've looked at the failure modes. Now we're going to start looking at the next, it might be this afternoon or tomorrow morning, what's the next step. And by the end of the course, maybe you can make your own decisions on that. But you can't have a guideline to tell you really. Okay, I think we better leave it at that. So thanks everybody. Give you another clap. So now, Ankel, you up. So we now got Ankel Locke to talk about some of the new technology or different ways you can do visual inspections without just walking around using your eyes. Ankel is the head of the dam safety section of the Norwegian Geotechnical Institute, and he's had a lot of experience in dam safety, including risk assessments and risk management of dams, instrumentation, surveillance, seismic analysis and design. He is a board member of the Norwegian National Committee on Large Dams. So thanks, Ankel.
Good. Thank you very much, David, and hello, everyone. So today I'll be talking a bit about special visual methods. That is a bit outside of the work I do personally at NGI. I work mostly with the risk part of our business these days, but we also have a group at NGI focusing on drones, remote sensing, these type of things that fits nicely into this context here. So I think first of all, just sort of defining what we're talking about when we say visual methods. I mean, the meaning of the word visual to begin with comes from Latin, so sight or to see. It sort of implies that we are using our eyes. It is a visual technique. When we then say visual inspection, it is that we are going out, we are inspecting the structure, in our case, a tailings dam or a water dam, primarily by using the eye. Right, so that is historically how it's been. We use tools to do this as well. If we want to document something, we use cameras. If we want to see further away, we use binoculars, right? But historically, it has been relatively simple tools. And I think the reason for this session here is that we're seeing now that our arsenal of these tools and what is considered simple is really growing significantly over the last few years in particular. So we now have drones, we have other unmanned vehicles, we have very high resolution, cheap cameras, right? And we have a very large number of small and lightweight, light enough to put on the drones, sensors. So we can measure and sort of, we're expanding the term what constitutes a visual inspection. But what I'll be talking about today is still sort of grounded in that is a visual approach. There is some form of using camera, or at least you need like a direct line of sight to do these types of techniques. We've seen some variations of these pillars of a surveillance program already. So ICOL has a version of this. The Norwegian dam regulations have a version of this. I think most regulations do some form of split between visual inspection, instrumentation, and some form of functional testing or checking. And that has been the case historically, but what we're seeing now is that we're starting to merge two of these. It's not given anymore what should be considered visual inspection and what should be considered instrumentation for some of these topics, right? Not everything. There's still piezometers is obviously instrumentation. Taking a photograph of something is obviously visual inspection. But where do you put INSAR? Where do you put satellite-based photos? These types of things. It's more of a continuous scale. So I do like Manuel's extra category here of campaigns or surveys. Right? Because a lot of these things you need to do them periodically. You can't do them continuously. Yeah. So when we talk about special visual methods, we're talking about non-conventional methods. So not a person going out and inspecting the dam on foot or by car, but we're talking about using something else. For example, that can be using some form of an unmanned marine vehicles. Maybe not so much for a tailings dam, but at least for a water dam. We're using drones that have some different names. I'll cover a bit of terminology as well. We can use cameras or a closed circuit TV. And we can use satellite-based sensing. So I won't cover the last two of these today. Cameras, I think, is a very well-established technology, and most people, it's sort of, you know, the basics. You put a camera on something and you can measure it, or you can see it and continuously. And we will have dedicated sessions on satellite-based sensing, like INSAR, later on. So I'll talk mostly about unmanned marine vehicles and drones. Now, I mean, all engineering is happening, and when it comes to drones and marine vehicles, it is especially complicated. There is usually some combination of these words on the screen here, right? But it's complicated because the V can be vessel, it can be vehicle, right? So, but any combination of these words here will give you these different. I'll try to explain. So first, on the marine side, we generally try to split it into two groups. So on one side, you have the unmanned surface vessels, which is like a boat, but it floats, but it's not. It doesn't have a captain, or it has a captain, but it's not on the boat. On the other side, you have underwater vessels, so that can either be an AUV, autonomous underwater vehicle, or an ROV, remotely operated vehicle. Now, the difference between an ROV and an AUV is that generally the ROV has an umbilical, so it is tethered to the surface. So you have maybe a compressor station or some hydraulic things up on the surface, and you're getting all the data and everything directly back, whereas the AUV can operate remotely without any link up to the surface, except for a radio signal to tell it where to go. So why do we use this? Well, they can see where we cannot. So generally, they can see underwater, which is hard to do. We can use divers. That is expensive. It is complex. There are HSE concerns. But by using these marine vehicles, we can then do it in a safer and hopefully more cost-effective way. Generally, what we do with these marine vehicles, we put sensors on them. Can either be cameras, or usually it's some combination of a camera and an acoustic sensor. So on the slide here, you can see the principle of how this acoustic sensor works. You have a sender, some type of acoustic source, and it sends a wave. And then when you have an object in the path of this wave, you get a reflected wave. And by measuring this distance and doing this repeatedly over large areas, you can then get like a whole surface model. You can then put different types of data then on top of the surface model, like a camera. I'll say this is a relatively mature technology. There are a lot of operators of these types of services, at least there is in Scandinavia. I think probably most over the world. So yeah, so it's not really rocket science anymore, these things. Some examples of what we can do with these marine vehicles. Photogrammetry is one. That is essentially putting a camera and distance sensors on either the underwater vehicle or the surface vehicle, and you couple that with a sort of positioning system, and you can get these surface models. So here you can see an example of a dam in Norway, where they've done both a above surface survey with a drone, right? So that gives you the riprap over the water level, but then also they've done it underwater and combined it into one model. So you have one 3D model covering both the above and below surface riprap. So this is used now quite routinely, I would say, for Norwegian dams to inspect the riprap on the upstream side. We have a lot of ice in Norway, and these rocks tend to be moved out of position when there's a cold winter. So then we can have an inspection also if the riprap happens to be underwater at the time of the inspection. On the sonar multi-beam echo sounder side, this is the acoustic, but it works in a similar way that you know the position of the underwater vehicle, and you then send acoustic signals and you measure the reflections. So this can be useful for scanning any type of underwater structures, like intake structures, like spillways, riprap, these things. You can also do this over time, right? So if you do it every year, you can identify trends. You can look for erosion. You can look for rock side of place, these things. But a couple of things to be aware, especially on the time aspect, is that you have to be sure that there is consistency between your surveys. We've had some examples where we've used one operator to do survey 1 and then another operator a year later, and for some reason they're not using the same coordinate systems. So we can't really identify any trends. We have to reset the whole baseline, which is unfortunate. Another thing to be aware is that it's really only useful in water, and I will also maybe say clear water. If you have too much sediment, that affects the speed of sound in water, and it tends to throw off these surveys. So the drone side, why do we use drones? I think it was covered a little bit already in the panel debate. These tailings dams in particular, they're huge. We're talking about potentially hundreds of kilometers of distance you have to cover. It's also not necessarily safe to send people out there. There is a risk aspect involved. So with drones, we can then, maybe not, I wrote replace here, but maybe I should take augment, because I don't think we're quite there yet that we can fully replace inspections with drones, and probably will never get to that point. I'll tell you why in a couple of slides. But at least we can replace parts of the manual inspections with these slides. So generally, they are a lot faster. You tend to have a camera higher up, so you can cover a greater distance in a much, much shorter amount of time. We have some examples from Norway where we've replaced manual tunnel inspections by drone flying, and we're talking about something that used to take days with people crawling up in narrow tunnel rooms, and now you can do it in a couple of hours with a drone. Another thing is that we can really couple a lot of sensor data together in these surveys. We don't just have to put a camera on it. We can also put other types of sensors. I'll show a couple of examples. And by combining this data and looking at it together, we can also get some additional value. So you can see some examples of drones we're using at NGI here. So they vary from very small, cheap drones that you put a high definition camera under, into these larger, longer battery life type of drones, where you can also hang more heavy equipment. I don't know what exactly the limit now is on the weight here, but we're talking well over 10 kilos that these larger ones can carry. So how do these methods work? Generally, you need to know the position of the drone. That is sort of the key. And then you have some type of sensor information from that position. And by doing this along certain grids, usually you sort of tend to fly in a grid back and forth to then cover your whole area. So the drone usually has sensors in it that gives you the kinematics or inertial forces, like it knows what angle it's pointing at, it knows how fast it's going, all these things. And then we use GPS or potentially some other georeferencing system to then know the exact position of the drone. And by coupling these with what the drone is measuring and storing the information and where it is in space, we can then put together these large models, be it either with cameras or lasers or whatever you want to hang under it. So I'll cover a couple of the most commonly used sensors that we have. So the most common one is a camera that gives you photogrammetry. We can also have lasers that gives us a LiDAR image. And we can also use different parts of the visual or the non-visual light spectrum that can either give us infrared, or we also sometimes call it multispectral, or we can look at different parts of both the visual and non-visual light spectrum together. But we can also, especially on these larger drones, hang more comprehensive sensors that can actually look into the ground. So we call that subsurface mapping. Those are usually electromagnetic types of sensors, either ground penetrating radar, GPR, or what's called transient electromagnetics, like electromagnetic sensor. So on the photogrammetry, how does this work? It is usually referred to as structure from motion. So it works similar to our eyes. Like if you cover one eye, you won't see any depth, right? But when you have two points of sight, you can then get the sort of depth coordinate of your model. So the structure from motion works in the same way. It's just that you have thousands of points and then take information in the pictures to then try to identify the same point from all the pictures. And then you put it together and you get the 3D model. There's a lot of software to do this automatically. It's not like the engineers sit and piece this together manually. The software does this for you. So what can we use this for? Of course, you can do a survey. You can map the as-is state. So here's an example on the right from a mine, a research program we're doing at NGI at the moment, where they're doing this for an ongoing mine. And on the left, you see an example of using it to map snow avalanche areas. So here we know the terrain model before it started snowing. We do that in the summer, and then we do the same survey in the winter. And you can identify how deep the snow is in different areas. You can also do this if something has gone wrong. So here's an example from a dam in Greece that failed. And by doing a relatively quick drone survey, you then get a full 3D model that you can then fly around. You can zoom into different parts to get a better idea of what happened. And that actually gives a lot of information that you wouldn't be able to do without having this model. I mean, one good thing about these surveys is that the engineer doesn't actually have to be out on the site all the time, right? So you can have a skilled operator doing this survey and then make the 3D model, and an engineer can sit halfway across the world and review this and try to get to the bottom of what happened. So this is an example that is quite unique to Norway. So in Norway, we have quick clay. I don't know how many is aware of what quick clay is, but it's a very, very brittle material. So it's a clay that if you stir it, it essentially loses all its strength extremely quickly. So on Manuel's graph of brittleness, it would be the most extreme case. It goes very little strain to essentially have a complete collapse, and you're left with just this soup. It has almost a water texture. So a few years ago, we had a major slide in Norway. It unfortunately took over 10 lives. And the reconnaissance or the post-event emergency response was quite complicated because this was an active failure. So we couldn't send rescue people in right away. So then there was continuous drone flights for over 2 weeks to identify where is the active failure going, how can we clear areas to then send rescue personnel in. So an example of where drones would then be able to see and make or give us information about places that weren't accessible by people. So that is sort of a as-is state, but maybe even more valuable if things aren't static in these dams, like things change over time. So we can do a sort of before and after. If you have one survey, in this case, it's in the mine. This is before a blast and after a blast. And then you can use some software to process this, and you can get an estimate of how much material has moved and to which direction and whatnot. We also do this to measure erosion over time. So this is a riverbank in a part in Norway that is quite exposed to flooding in the spring and autumn. So by doing these types of surveys repeatedly, we can then see what's the effect of erosion over time. So here you can see the colors represent how much material has moved. So darker colors is more change. And you can see where I've drawn this cross-section line here, that the top is essentially moving down and the bottom is coming up. So there's an ongoing tendency for a small slide in this part. And there is this is not a huge area, but there are some benches and sort of a hiking rest spot at the top here. So they're worried that this might fall into the river. And they're probably going to do some ground stabilizing efforts to prevent this erosion from happening further. All right. Other sensors, lasers, LiDAR. You've probably seen some of these shade relief maps. That gives you a very accurate terrain model. So with these LiDAR scans, it works similarly to the photos, but except you shoot with a laser instead of a camera. So this also gives you a point cloud model, and by doing this over time, you can identify changes. So on the right-hand side there, it's what we call operational avalanche maps that shows you changes in snow depth over time. And you can use this to identify risk for snow avalanches and other things. And the same principle would apply to doing it on an active tailings dam. For example, you can look for deformations in the surface. You can look for changes on the beach if design is according to plan, or if the operations are according to design, and these type of things. Thermal multispectral. So this uses other than just the visible part of the light spectrum. That has some applications. We can look for, especially wet areas tend to be colder than dry areas. So if you look for signs of colder temperature, you can use that to at least indirectly identify wet areas and high phreatic lines and these type of things. It's good for looking for leaks over a large area. The leaks tend to show up as hotspots also in the temperature. And also with certain parts of the visual spectrum, we can also use these to classify different chemicals. So various forms of chemical concentrations tend to have different colors. So if you have a high concentration in some areas and not in others, they tend to show up as hotspots as well. Another example where the same technique has been used to identify wet areas and potential high phreatic lines on a levee in Michigan. But it is basically a camera that looks at slightly different parts of the light spectrum. The last part, and maybe the least used so far, is subsurface mapping. So these ground penetrating radars have now gotten so small that they can fit under a medium to large drone. A GPR has this limitation. You can't see, due to the frequency of radar waves it uses, you can't really see that far down into tailings. It depends a bit on the material. But generally, you can look for anomalies, in particular on the moisture content. So if you have a leak or some type of abnormal water concentration in the top of your embankment, that can be picked up by these types of sensors. Related to this is the transient electromagnetics. So this can see deeper into the material, but generally the resolution is a lot lower. So it's a bit limited what we can then use the data for in terms of inferring different soil properties. But what it can be used for is to give a high-level indication of what type of materials we're dealing with. So for infrastructure, we're using it a lot to identify the depth for bedrock, which is a critical parameter if you need to remove masses or drill piles to bedrock, these type of things. And it can also be used to correlate to at least some geotechnical parameters. But I would caution that these correlation models aren't terribly good. And it depends a bit on what type of materials we're dealing with. But generally, you can identify whether you have thick clay or whether you have sand or whether you have bedrock, like on a quite high level. The value from this really comes when you also have borehole data, because you need to triangulate these models with actual ground truthing to get a large ground model. Right. I want to sum up. So what's the benefit of using these drones and marine vehicles? They allow us to see what we can't see with the naked eye. They can go where people can't, and they can cover large areas in quite a short time. We now have a large number of these sensors that can be combined for better value. This used to be quite expensive, but also this is rapid developing technology. So the prices are generally coming down, even though still some are more expensive than others. Last slide, there's also some potential pitfalls here. I would say generally you need to have very skilled operators that can really make or break these types of surveys. There are regulations on what you can do. In Norway, there is tons of regulations on where you can fly, how high you can fly, who can fly, these things. We have weather limitations. You generally need a line of sight to do this type of thing. So if there is very foggy weather, there is limits on what you can do. If there's high winds, you can't necessarily fly. If it's raining, these type of things. And last part, the last bullet here, I say do not underestimate the complexity of managing these enormous data amounts. This is not single points in space, right? We're talking about continuous point clouds. We're talking about potentially terabytes of data. So it's not a easy task to actually make sense of all this data and turning it into the engineering parameters that we are interested in looking at, and what is at the end of the day, what gives value to the dam owner or authorities or whoever is going to use the data. Good.
Okay. Okay. We are running a bit over time, so we might just hold the questions. We're going to move on and we'll have a Q&A session a bit later on this afternoon before we wrap up. So you hold all the questions until then. So now I want to go on to session 4, basically established technology, chaired by Caius. And we're about 3/4 of an hour behind time, but we're going to have coffee break in half an hour after this first couple of presentations.
Thank you, David.
Sorry.
No problem. No problem. So, give me a little second here.
Want me to introduce the speaker? Because we basically got the surface
Vijay and Matt.
I can introduce those, then copy back and introduce them after.
Yeah.
Okay. Want me to do that now?
Yeah.
Oh, so I haven't got anything on VJ. You have to introduce himself.
Yeah, Vijay. Oh, anyway, so
And Matt.
Matt is coming after that. Yeah. So we're gonna get into a session that's quite interesting here. We are talking about established technologies, and we're gonna have quite a few presentations. No, we don't have a slide on that because I just wanna get going with the presentations. So Vijay, are you here? Please come over and session 4. And Matt is coming right after that. So yeah. So we're gonna do the presentations, and at the end, I'm gonna bring everybody in the front, and we're gonna have a Q&A section. Would you like to introduce yourself?
Yeah, sure. Hi, good afternoon. Myself, Vijay Chandel. I am the product manager in Hexagon India, and I look after the reality capture solutions and the monitoring solutions in India right now. Monitoring solutions, basically, not only the dam, a lot of monitoring solutions are there. Right now, we are also working in some of the monitoring solutions where avalanche and landslides are also there. So today, I'm going to talk about the surface survey monitoring. So just to give a brief about Hexagon. So we are a reality technology company, and we are into various autonomous solutions right now. And we have a very good presence in globally as well as in India. So our divisional structures are everywhere. We are everywhere. We are into MI, manufacturing intelligence. We are in asset life cycle, geosystems, autonomous solutions, and safety infrastructure. In India, we have offices at all parts, and we have a lot of employees. We have good R&D centers in Pune, Hyderabad, and Gurgaon for different kind of solutions. So as Hexagon India, we are involved in a lot of bigger projects from the government of India. And we are working with government of India to establish a lot of projects and the solutions. So you can see in this, and already we have worked on some of the dam solutions, the structured dam solution in INCO and UVNL, and Also, we have established a lot of coast stations all over India, and you can see we have a good base in India right now. So, morning first session, we just saw that everybody was talking about the failures of the failures. So how this failures, how to come over this failures. So today I'm going to talk about the monitoring for the structure monitoring. So what do you mean by monitoring? Means monitoring I am talking about means how much movement is there in the structure right now, how fast it is moving, the acceleration, how the total movement since the beginning means the beginning what was there and right now what is there and might be in future what can it cause. It can send the messages, it can go with the legal claims and all. So as an hexagon geosystem, we have a lot of monitoring solutions in our systems. So today I'm going to talk about that monitoring solutions which are already established right now, and already we are working in various places with these monitoring solutions. So if I talk about hexagon, we have a long history in monitoring, and we started from T3. It is long back in 1800s and 1900s, and we did that. And so today, in monitoring, I will be going to talk about the geodetic monitoring. Geodetic monitoring means the movement which is happening there. So what is geodetic monitoring? Geodetic monitoring generally complies with the various hardwares like TPS, GNSS, which I'm going to talk about in my next slides. And it generally captures the motion in the structure and gives you the messages if it goes beyond the limit or something. So these are some of the geodetic monitoring and established methods which are right now getting used in India right now and in different part of world. First is the TPS solutions. It can be TPS can be manual, it can be robotic, it can be monitoring solution, whatever. Then the tilt meters, GPS, and right now the solutions which we are a lot of things are going on with the scanners which are in the total station as well as the normal scanners, the P50, the robust type of scanners, the survey grade scanners. So today I will start with the TPS monitoring instruments. TPS basically it is called total station, it is called monitoring total station, it is called distance measurement total station. All the you can give whatever the name. It basically takes the XYZ coordinate of a particular location and gives the displacement on that location. So just an example you can see in this video that this total station is a robotic total station and established at some point, and it has given one frequency, means every 6 hours you have to take these points at different locations and different points. So it is taking that that particular location point in every 6 hours and giving the displacements. So how it does? It will first, as for example, I have just started my total station at 12 o'clock and I took the reading at 12 o'clock, and then at 6 o'clock again that reading has been done. So whatever the displacement will be there, it will get recorded and it will come down to your system wherever you have installed. It will come down to your control center, it will come down to your mobile phones and wherever you want. So what is the typical setup? Typical setup basically starts with the total station. It can, again, I'm telling you, it can be manual where person will go and he will do the measurements and come back. It can be robotic where you will install the total station and you will give the frequency 1 hour, 2 hour, 5 or 6 hours, and it will just take that point in particular frequency and come back. And then we will install the prism or the the prism cactus on the dam structure where I see that that will be the critical setup will be there or critical point is there, and some reference point will be there which will be from the GNSS or can be from the total station. So every 6 hours or 1 hour, 2 hour, whatever frequency you have sent, it will just take the point and it will again take the point in 6 hours, whatever you have set up, and it will give you the displacements. So whatever the displacements you have fitted in, if you have seen that up to this extent it is okay, but after this it should give you the alarm. So it will give you alarm if the displacement is high or it has passed the limit. So this is a total station method to get the structural deformation or the analysis. So you can see here that in example in the back office software, it looks like that red is the displacement which is beyond limit, and you have to act on this. So this kind of report you will get, and the alarm will be generated. The second part of this, after the total station, the deformation, the second part, which is commonly used for the surface monitoring, is the GNSS monitoring system. GNSS, the common word is Global Navigation Satellite System, or we say GPS. But these are GPS are not the Google GPS or some kind of GPS. These are hand GPS. This gives you a millimeter accuracy according to different projects. So also, this is the workflow if I install a GPS or something. So you can see the antenna, and the below is the receiver. Below is the receiver, means receiver are the very high-tech receivers, and it can track each and every satellite location, satellite signals in their own. And that antenna gets installed in different parts of the, instead of Prism, you can install these antennas and you'll get the GNSS frequency out of there. And in the software, then you can bring in the data, and then you can again get the data in your control center and the mobile phones wherever you install. So this is just an example that how it look like. This is the GPS, and these are all the signals which you are getting from different antennas time to time, and it is getting calculated according to the displacement, and it will give you the graph again in the same format which you require, and again you can set the limit, and after that, if this limit gets crossed, and you will get the alarm system. Third, which I was talking about, is the scanning system, where you can use the total station scanner, which is getting installed. These are the scanners which again will scan which again will scan time interval like 2 hours or 3 hours, and give you the deformation monitoring as per your requirement. So this is one example that this area has getting scanned in every 2 hours, and with using the software of the online analysis and the software reporting format, you can get the analysis, whatever the displacement has been there. Like you can see the color mapping, the red is the displacement where it has happened the most. So it is a critical there. So you can just act on that. So this is the scanning methodology. Then tilt meter also pays, because everything with the total station or GNSS can give you the displacements, but for the inclination and all this data where you require, you can go for the tilt meter, and this tilt meter gets installed and give you the inclination of the inclination output of the dam. So why I'm showing this, because all this data will get merged to single location with the help of the back office software. In Leica case, it is a GeoMOS. So whatever sensors you have installed in your dam, these are all the surface sensors which I am talking about, but there are the sensors which are working behind the scenes, like weather station, water level, piezometers, everything. So all this data will get analyzed with this surface sensors data, and will give you a report, the bunch report, which can be analyzed on the back office software, like GeoMOS or whatever you say, means the third party softwares can also work. So this is the methodology I'm just talking about. The workflow will be the data collection. The data collection will be done from various sensors. It will get integrated with the different kind of sensors which are installed on the dam. It will monitor, it will collect the data, it will process the data and combine the data, and will give you the final output as per your requirement. Means I will say the visualized report or message alert or the SMS system, the alarm system, or as per your requirement. So this is basically the workflow. So this is from my side. Thank you.
Thank you so much. We will call you later on when we have a question period, so thank you. Just quickly want to introduce Matt Sullivan, currently sales manager at Geocon, with over 20 years experience in geotechnical monitoring and a background in geology, which is always very useful. Please welcome.
Thank you. Right. Very much. I'm here to talk a little bit about piezometers and some settlement systems. So if you're not familiar, I think most of you probably are. I just want to talk a little bit. Is that better? Okay. Yeah, so piezometers, if you're not familiar, you're going to be using them for monitoring your pore water pressures or any kind of flow pattern you're looking for. I think most of you are aware of this. So I really won't, for sake of time here, just brief applications. There's many, but I think in this case, dams and slopes are probably the biggest things that we're probably looking at here, where we can use, piezometers at various different locations. So I'll just briefly get into the different types, and I don't have all of them listed here. There are so many different types and applications that we can do. But you have standard piezometers, for example, the manufacturers, we all make them. They generally will work up to about 3 MPa range. We do make others past those ranges as well, but they just usually incorporate a different body size or different construct of the instrument itself to handle those higher pressures or lower pressures, depending on what you're doing. And here we just point out the general diameter is about 19 millimeters. We have and the standard piezometers too. I should just mention briefly. So they are unvented, so they are they're sealed, and they're going to read total pressures. They're going to read not just the pore water pressure, but they're going to read atmosphere as well if you're hydraulically connected. We do have many of the manufacturers make vented piezometers as well. These are basically designed that they have a vent tube accessing the backside of the diaphragm of the piezometer, therefore equaling out the atmospheric pressure, giving you the actual pore pressure or water level pressure. These are typically used, in open sandpipes applications like that. There are some that make smaller diameter. Some of your sites may have, especially if you're inheriting an older site. Some places have smaller diameter wells they put in traditional monitoring with a water level tape or something like that. In some cases, people want to automate those, so there are some smaller sizes available from the different manufacturers. There's push-in type piezometers. These are designed for using with either with a drill, but you're more of an in situ installation. So you typically you may drill down several feet or meters, and you want to push it, say 1.5 meters or so. You can just drill down to about 1.5 meters above where you want to put it. You push it in, and they're designed such that they have a left-handed thread that you can spin off the drill rod and leave the instrument in place in the ground. We also design, several of us have versions that can be used with CPT rigs. So they have a smooth back that you can easily just slide the rod over, push it in place, and pull the rod out. I will stress when you're using these types to be sure you're monitoring during the pushing process. You don't want to overrange the instrument during that process. There are also semiconductor piezometers. These previously, I guess I'm getting ahead of myself here. They're all vibrating wire style instruments. If you're not familiar with that, it puts off a frequency. Where you have some systems where you want to use semiconductor. Maybe you have an existing system on site to monitor with. It's a SCADA system, or it only reads analog output type signal. So these can actually work for 4 to 20 milliamp millivolt per volt, 0 to 5 volt DC. And they can be packaged in the different ranges as well. I briefly just put here too, they're barometers. So you have the analog output type, there is a vibrating wire type. I recommend if you have the non-vented versions that you use a barometer on site if you've got shallow applications or open well applications. This will help you convert the data appropriately. At least have one barometer on site. I did not put it on the slide, but I do want to mention the manufacturers do make corrosion resistant type piezometer bodies as well. So that is something to consider for tailings, I think. Depending on the makeup, the chemistry of what you're putting it in, you know, there are options. There's titanium, there's Inconel, there are other metal types and alloys that can be used. I would suggest you just contact the manufacturer and discuss it with them. Keep in mind, we're not metallurgists, so we probably will need you to have some analysis of the material it's going into to help better suit the type of material. I just wanted to touch briefly on some of the considerations that you may want to do. First of all, before you go out to the site, you know, make sure that you're checking your device, make sure it wasn't damaged in shipment, make sure it's operating properly. You know, have your handheld readout, make sure you've got it reading correctly in the right position. These vibrating wire instruments, you know, run in different ranges and frequencies, so you want to make sure you select the correct range to sweep. And then you know, basically you also want to just make sure that everything's functioning properly before you put it in the hole, because once you put it in the hole, you can't really get it back usually. Also, just a couple tips on saturating. You know, it is very important that you saturate and get a zero reading. I think most of you probably know that, but we've had instances where people call up and they've either forgotten this step or they weren't aware of this step. It's a very important part of the process. It kind of finishes the calibration, if you will. It basically, so what you want to do is you want to saturate, take your zero reading. So you saturate the tip. Typically, most of these, the tip can be pulled off. You saturate it in water. When you're ready to install, you're going to place it down the hole and then take a zero reading. So there are two methods to zero, and I apologize, it's kind of a lot of words there, but the first method would be ideally that if you know the water level in the borehole, you're going to put your piezometer just above that water level and take a reading. That would be, you know, the closest zero you can get to that surface. And you want to do that because you don't know what elevation you are. You know, there's all the manufacturers have a zero calibration they do at their facility. But for example, where we are in New Hampshire, eastern U.S., you know, we're 500 feet above sea level, whereas, you know, here you may be different. You may be, you know, 5,000 feet above sea level. That may very much change the way the zero reading happens. So that's why we do the zero. And the second method is just a little simpler. A lot of times people are not sure of themselves if they know exactly where the water level is down the hole, or you may have drilling mud or fluids that are down there, and they may start to touch and contact with the piezometer. So a lot of people will just take a bucket above at the borehole, soak it, pull it out of the bucket, and take a reading, and then put it down the hole once they have it. So one of the things I will caution you on when you do that, when you pick it up, don't grab the body of the instrument because that can alter the temperature as well. Just your hand, the temperature of your hand. So just keep those types of things in mind when doing that. There's a couple of different installation methods. So thank you. Somebody's drilling. They're installing. Yeah, they're installing. That's right. So, and some of you may have heard that. So there's the traditional installation method with just sand pack. So typically, what you would do down the borehole is you'd have maybe a meter of sand pack that you put the piezometer in, and then maybe another meter of bentonite seal, and then grout the rest of the borehole, and go from there. You know, after you've saturated the instrument itself. So this is the traditional method. There are pros and cons to both, I suppose. The other method is the fully grouted method, where basically there's no sand pack. You've saturated the filter. You put it down the borehole, and you've constructed your grout such that it matches the surrounding borehole material. This is important to know this. We get a lot of calls asking us, you know, what should the grout mixture be? And I'm going to respond back to you. Well, your engineer of record really should be the one to determine that. You know the site conditions, you know the material it's going into. We give basic ratios to help you, but that is something that generally you guys are in charge of doing. and making sure you know. I'd say too, during this installation type, be careful when you're jetting that grout down to monitor your sensor. You don't want to overpressurize the sensor again during that process. So I know that was kind of quick, but I know we're a little short on time, so I'm going to keep moving. They asked to talk a little bit about settlement systems. So there are a few different types, but liquid systems are most commonly used. And basically there's conventional, there's borehole types. So, and then we have the liquid level gauges as well. So these, for example, these liquid level gauges, they're typically used in differential settlement monitoring. They're constructed with, either a displacement transducer with a hanging weight or inside of a fluid that's vented. So you get high accuracy you tend to get more high accuracy with these types of instruments. These are the different applications, but I think I just touched on those. A lot of buildings, a lot of, structural monitoring, I would say. And then you have the single point systems, which are liquid based. Basically, it's a pressure transducer. Where the pointer is here. So this is your pressure transducer here. It's attached to a plate. You want to level that plate in a trench, and then you want to trace your liquid filled tubing along the trench, typically at an angle going upward toward a reservoir, which you don't see here, but the reservoir is basically installed in stable ground that you don't expect to be moving, because that's basically what's happening here is you're having a head pressure differential. So the plate should move. It's going to move in reference to the reservoir, and that's how we're going to pick up the different readings. The disadvantages of this system can be that if you do not protect that liquid filled tubing, liquid is affected by temperature very much. So it can actually show possibly heave or settlement when it really isn't that. It's just a temperature change. So it's ideal with these systems if you can put it in early before you do any work, get a baseline reading that you know how the instrument is performing in just the standard day to night ratio, for example, or the temperature swings of the day. So that you have a good baseline to read with. I just caution when you install those that you try to protect that from direct sunlight as much as possible. And have the expectation to know that these systems are not, they're not fine precision, but they have their applications for gross movements. This is just kind of another visual just to show kind of how this would be your reservoir type setup here. Another method to do this would be to put it into a borehole. So we're kind of flipping it on its head a little bit. This is your reservoir here, and then you have your sensor here, and then there's your settlement plate. So you drill your hole down to a depth where you know you don't have either bedrock or non-compressible material, and you're going to cement grout that sensor into place so it's fixed. So the sensor is now your fixed point, and then the reservoir and the plate will move up and down in relation to the sensor. The advantage of this is that everything's in the borehole. You have less temperature effect, and you have less chance of machinery and whatnot clipping your line or clipping your reservoir off to the side. So the only thing you really have coming up out of the hole would be your signal cable back to wherever you plan to put your readout. Disadvantages: you have to drill a borehole, so more cost. But these are nice for systems where maybe you're having levels of fill. You can go out and put this in, put your fill down. You don't have to worry about moving things or anything else. You can just continue on. This is just another application, and we can do multiple systems as well. So you can put multiple units downhole with an anchoring system, so you can do multiple level as well. That's another option. Another version is a manual settlement profiler, where you typically use this, as in a horizontal pipe. You can run this through. We call it a torpedo, but it's basically got a sensor on the end with liquid filled tubing. Again, this whole device here is mounted on a tripod. So if I'm here and I'm going to run it through, I have to run that line through, and then I have to pull it to each position I want to take a reading. It's portable, so that's an advantage. You can reuse it. But some of the disadvantages are you have to be able to pull that line through effectively. So sometimes you need a pulley system to do this, depending how long your run is, it can be a challenge. Again, it's also liquid filled, so you have temperature to contend with. I think I already talked about these a little bit, but these multi-point systems here, like I said, I already talked about it, but it's high resolution. These are chamber style, and these are pressure sensor style here. So this is more mechanical. It's got a hanging weight inside on a displacement transducer that hangs in liquid, whereas this is a pressure sensor. So basically, it's just a diagram showing how the settlement, how that works. And so you basically, one of the challenges I'd say too with this type of system here is that you do have to have a fixed point that's a reference. So if you don't have that, these systems can be a challenge to install, or you may have to run a long distance. So if this whole room was settling, I'd have to find a point outside the room to connect all of that to for reference. So how's that?
Good.
That was quick. So we're gonna have a quick coffee break. I would suggest that we limit that to, well, we had 25 minutes. Let's do it 15 minutes. Right? So I would like, can we squeeze it to 13? So maybe 4:25. 4:30 maximum, we're gonna get going, okay? And after the break, we're gonna have Pierre from Canada, Greta from Italy, and Sam online is from Sweden, I believe.
Yep.
So, and then we're gonna have a nice panel discussion on these instruments. So let's go for coffee.
Did you see from Sam? He want to try his presentation now. During the break.
Hi Sam, you share your screen. How we got? We don't have Sam. How can we get Sam? No.
Isn't this a mic?
Yeah, hold a second. Can you? It should work both way. Hold a second. I'm just trying to set up the sound here.
That was a good test.
Yes. Are you on mute, Sam? Or are you speaking?
I'm not muted now.
Trying to talk? Okay. No.
I think
All right.
You should check that it's that this is. There should be two.
Yeah, it's in the speaker.
Yeah.
I know the Java.
Yeah, bro.
Okay. Trying to speak now?
Yes, I'm trying to speak. Can you hear me?
No. Sound is not coming through.
Okay.
Hold a second. Let's see here. Why it's not coming?
Can you see my screen?
Yeah, I can hear you now. Yes.
Okay, and can you see my and can you see my screen?
Yes, we can.
Okay.
Yeah, the question will be why these Microsoft now are not working.
Was there before.
Yeah.
So we
No, hold a second. I talk. Just Sam, can you speak?
Yes, I'm speaking. Do you want me to sing also?
No, that's it. We got you. It's working.
Okay, perfect. Then we know that everything seems to be able to work here also in the next hours.
Okay,
Perfect.
See shortly.
Yeah, bye.
Okay, bye.
Thanks a lot.
Which one is it? 27?
No, it's this one.
Technology is running.
Yeah.
You are first and then Greta is. Done, off and running. Fantastic. Now let's quickly go. Yeah, you can. Yeah, no, I don't.
Yes. No, it's a good one. Should take care of possession. This yeah. So I think it's huge, and it's just more than that. So I don't want più o meno
I'm always taking that. Genuinely, I've been on the side too. As you call it, what was
CPT. Yeah, so one, just push your push, and just do a nice slow push. Monitor that. But we're still on.
We're just.
Did you?
But the vendors that use, like, yes, they actually, they don't use the washing style with, they put it inside. Like, it's on the steel tube to protect it. It has sand in that side.
Okay.
Inside it.
Interesting.
Pretty,
So what I like about pushing stuff is the movie, the blue movie. Yeah, the vents are on the with right on top, it goes both. Whereas the other style of threads, sometimes if you're soft material, a lot of times with alcohol. But so that will dissolve. But it would protect during the pushing distance. And eventually it'll just dissolve the membranes. That's one easy tip. But that's it. Somebody or something. I don't tell you that should. But we can discussion.
We need to explain. Also, I guess, incident is already so small. It's just we still have CPT. It's just really hard to see very responsibilities. So you just same cost of these. They're all the same.
Yeah, that's a good point. Yeah, I mean, like nested. People like to use the term, just take the term, which is fine.
Okay.
Right, but when you take the cables, don't bunch them all together. It's not even creative conflict between the cables. You'll communicate. Yeah, so we always talk about chart space. But then also the other ones with just one key. You have three sides. So those are one bus cable. It's so it's one single key, and then you have the so yeah, and I've used those. Yeah, I've never tried theirs, but I have. No, I actually have a photo on the presentation. The great exit. So at the toe of the dam, you really have a lot of like the exit grade. You really can see the vertical grades, and in some areas maybe it's and really have different formations. You can really see where that is really essence. And it's just one cable. So and within the tailing, you have a lot of you need to have whatever, even if it's in the same 2-3 years, but that area you want to have several problem is in this you're so that's it. So that's something that I want to mention. Definitely. We've had lots, just, I agree. Like, it's just, but yeah, I'm looking forward to it. Yeah. That's just gonna help. And some. Ah, why is it so full? Full? Oh, that make me just the engineer. Yeah, I haven't felt good. Yeah. I'll be right back. Yeah. I should have thought that. I'm always telling my kids, so, yeah, the house, but I just don't let go. Yeah, exactly.
So it's interesting.
That's all. It's lots of. It's 16 mil.
Okay.
And then they've got an internal tube, which is. Okay. 20. So it's based on 5 days. So
Yeah.
They go down, the bottom, basically. A little bit of the other side, it's wax. And those wax. Yeah. Like, yeah. That is something that I had to change the shape of the back, just slot onto these with the rock. So you actually.
Usually they love the kid.
Yeah.
Sure. You get those from. There are agents. We tend to most things. Really? You ever experienced flaw? I've had.
Yeah.
I've seen it one time.
They overloaded through.
Yeah.
It's
easy enough to do if it's not paying attention.
To the case. That's
Really?
and one. Yeah, one. We need those 3 first. 2, you could actually see what's close to 6. And then there's a third. Check and find. Test it.
Usually it would be that it just goes. It's just the wire breaks.
Okay. Yeah.
Just caution there, just the.
So it's
Yeah, exactly. You come to India.
settle. All right. We put everything.
Okay, who we go first? Pierre, yes? Pierre and then Greta. Yeah. We already had your presentation here.
How did it go with Sam?
Yeah, it's done. We check it, it's fine.
Okay.
Yeah.
Yeah, I got it in there.
Okay.
It's ready to go.
Perfect.
No.
I'm told yours.
Well,
20. We can do it. Not 20. All right, 21 will be, is effectively. Push the button. No, that was all up there.
Okay. So shall we get going? So next, please. Just coming? Yeah, coming.
No, Sam, if he's going first.
Yeah.
Yeah.
So we have Pierre Choquet. So there are insights. Let's move on. We are 1 minute over, so we can get going. Pierre has been involved with the geotechnical instrumentation monitoring for almost his entire career. He joined RST Instruments in 2007 and is now technical advisor for Terra Insights since 2021. And he's a graduate from École Polytechnique in Montreal and doctorate degree in rock mechanics from École des Mines de Paris in France. And definitely, Pierre is also, I can say, very proudly, he also assisted me in one of the courses at the University of British Columbia for many years in helping me teaching the new students on instrumentation. So I really appreciate that, Pierre. And without further ado, presentation is ready.
Thank you, Caius. Good afternoon, everyone. So I'll present to you today on the topic of inclinometers and interpretation of inclinometer measurements. And these are the various topics I will cover. Metrology, installation, interpretation. I'll talk about in-place inclinometers as well and strings of tilt segments. And maybe some of you are also interested if I say a few words about TDR, time domain reflectometry. So I'll give a few words about that as well. So inclinometer surveys, I think that many of you or all of you are familiar with what they are. So the idea is to monitor slope movements by putting an inclinometer casing, a tube basically, into the ground, all the way down to a stable horizon. So you're trying to anchor the casing in an area in the ground that will be your reference. And then you're running an inclinometer probe in the casing in order to establish a horizontal deformation profile. So I'll show that in 1 second. And inclinometers are usually used in conjunction with piezometers, crack meters. That means complementary geotechnical instrumentation as well. So this is a typical and maybe a little bit ideal inclinometer profile, but it's a true inclinometer profile. It's a real one. It's in rock, so that's why the shear zone is so defined, but it's a true inclinometer profile that once we were reviewing. So the way that we display inclinometer measurements is an accumulated displacement profile, which is the actual horizontal displacement. So the scale is the y-axis is the depth, and the horizontal axis is the displacement. So you can clearly see that the bottom of the casing is very stable, and then the shear zone, that's where the displacement is happening. The other plots, like the one, I have a problem there. The other plots are the incremental displacement, so that shows you at what depth the displacement is happening. The absolute position, which is the real shape of the casing. So though here you see in that case that the casing at that depth was slightly not vertical, but slightly inclined, but this doesn't interfere when it's a slight curve like that. It doesn't interfere really with the inclinometer measurements. And this is here something very important that I will come back to, the checksums, in order to assess on whether the data is accurate or not. But I'll come back on that. And you can also plot the crest displacement, the colored displacement of the inclinometer. So that's another plot of inclinometer data, just to give a more example. And that one is for the abutment of a future dam. You see the river here. And as the diversion tunnel was being excavated, a big block movement started to happen. A big concrete block was built to stabilize this big slide. And as you can see here, the depth at which the displacement was happening. And you see that with time, the contractor was able to stabilize the slide. So that ended up with good news, basically. So where do we use inclinometers in dams? So they're used in embankment dams, in tailings dams. They can be installed. Well, here you have an example for a water dam with a cut-off wall that was actually installed through the whole length of the dam, probably because there is no earth core. So the idea was to provide an impervious curtain in the dam. And I find it an interesting way of displaying inclinometer data. Actually, there is one inclinometer casing here, another one there, another one there. And if you're able to make things visual like that for the readers, it's a good thing, actually, because you realize where the different geological horizons, where the inclinometer is located, and the displacements where they are actually happening. So a nice way to display things. They can be installed, well, here in that case of this tailings dam, they can be installed for this upstream construction. They can be, downstream construction. They can be installed from the crest of the starter dam, and as the downstream construction is happening, you can install additional inclinometer casings in order to monitor the potential failure surfaces. So in terms of bibliography, there is an ASTM standard and an ISO standard on inclinometers. So that part is well covered in terms of bibliography, and there is a bunch of literature also that has happened over the years on inclinometers. This is more a metrological slide. I always like to say that the tilt is a powerful measurement because it's very accurate and repeatable. Take the example of a pendulum, for example. If you consider a pendulum for a concrete dam, if you consider a pendulum, it can be up to 50 meters long, very easy, or longer. And if you're doing a measurement with the pendulum, which is very easily feasible, repeatable at 1 millimeter, that means that you're measuring one part in 50,000. And that's way better than what any other type of instruments, which are usually, when they're 0.1% accurate, which are one part in 1,000. So tilt is very powerful in that sense. And the smallest tilt angle that you can measure with tilt meters, independently more or less from the manufacturers, is in the range of 0.001 degree or 0.002 degrees. So that would be equivalent to 1 part in 33,000. So very close to what you were achieving with the pendulum. Nowadays, most inclinometers are based on MEMS, micro-electromechanical systems. So these are the accelerometers, more or less the same that you have in your iPhones, except that the way that they are read is more repeatable, if you will, and lends you this 0.002 degrees that I was mentioning before. So it's a very accurate, capacitive distance measurement on the silicon components that are on cantilever. And as the tilt meter moves, you have very small distance changes that are measured with a capacitive principle. So it's actually surprising how accurate it can be for a little silicon chip, which is about 1 millimeter by 1 millimeter. So the typical specs, I mentioned them before. So the inclinometers, in-place inclinometer, tilt meters, they can have a repeatability of 0.002 degrees. And the most common MEMS instruments are the manual inclinometer systems, with whom many of you are certainly familiar. In-place inclinometers, strings of tilt segments. I'll come back on all those in the next slides, and then tilt meters. I think that the majority of the inclinometer readings are still done in the world. I will say are still done with manual probes. Maybe quite a few of you could confirm that. I'm in favor of automated measurements, so I will cover that topic as well. But the reality is that most inclinometers are read with manual inclinometer probes. So typical inclinometer systems, as you see here, look like that. That means there is a probe with wheels that would be lowered into the inclinometer casing. There is a cable, a signal cable, in which a lot of the magic sauce is actually incorporated in terms of having a very robust cable that will not stretch, with reference marks that will not move. That's very important for the accuracy, the repeatability rather, of the inclinometer measurements. All of this on the reel, and nowadays the reel transmits by Bluetooth, by radio. That means to a portable readout on which you're collecting the data, but you can also plot the inclinometer profiles to verify in the field that they are valid, that they are repeatable, that the checksums are good. And the inclinometer casings themselves, the industry has standardized to 2 diameters, which is a good thing, and also has standardized on grooves, which is a good thing. That means that the probe from manufacturer X can read can be used in the inclinometer casing of the manufacturer Y, and so forth. So there is standardization in there, and typically, those casings are 3 meters long, it's written somewhere here, yeah. And the couplings are either of the quick connect type, that means with an O-ring and you just snap them together, or you can use glue, an adhesive and ABS cement on the couplings. If you're considering inclinometer casing longer than 50 meters or something like that, I strongly recommend to use glue on your couplings, because couplings and an inclinometer casing are the weak point. If a casing will fail, it's usually at the couplings. So it's important to make them very robust. Now, an issue that happens fairly or relatively often is the embankment, the tailings dam in which you're installing the inclinometer casing, is also settling vertically. There is some settlement happening, and the inclinometer casing can take some compression, but not more than 1%. So that means that as you're raising the dam, if you're compressing the casing too much, then the casing will fail, usually at the couplings, and you won't be able to run the probe anymore. So to accommodate that, you can use, I really have problems with my remote. You can use a telescopic casing or telescopic casing sections. That means lengths of casing that can accommodate the settlement, and they can actually collapse by up to 15 centimeters. Except that inside you might have an issue with that if you're using a telescopic casing, in the sense that the wheels of the inclinometer probe might end up in a situation that you see here. That means one wheel in the groove and one wheel outside of the groove. And then all of a sudden you're giving 2 degrees or 3 degrees of inclination to your probe, which will screw up, in principle, all your measurement. If you're lucky, you can have this situation that you see here. That means that yes, you have the wheel which is outside of the groove, but when you do the 180, most of you are certainly familiar that you do the inclinable surveys two times, you reverse by 180 degrees the second time to get rid of the systematic error. And if you're lucky, the wheel might end up in the opposite direction. And in that case, you might see a little jump in your cumulative displacement profile. That's an example here where that thing is actually happening. And you have a jump of 2 millimeters of displacement. So if you know it, you won't panic when you see that. You'll understand that this is what has happened. Another option is to use the traditional standard casing with external couplings. That makes the couplings more robust, and then you might be able to accumulate that 1% vertical settlement. Now, in terms of specifications, most of the inclinable systems, they have similar specifications. That means a system accuracy of 2 millimeters per 25 meters of inclinable survey. That means that if you conduct the survey, you'll be repeatable one time, and then the second time you'll be repeatable within 2 millimeters of 25 meters of casing length. These I will skip, just example that show you that you can get that repeatability quite easily, actually, if you operator are really following all the steps to do proper inclinable measurements. This one I will skip also. I mentioned before the checksums. Those of you who are also familiar with inclinable measurements know that when you do those two surveys at 180 degrees, when you take the average, it's the true inclination, and when you take the difference between the two, it's the bias, it's the little systematic error in the probe. But these checksums should be constant, as you see. So that's an inclinable profile in the A and B direction. And those checksums should be constant from one survey to another. And this is what guarantees you that the survey is correct. I'm not concerned when I see spikes like that if I am on the scale of plus or minus, you cannot read it, but it's a scale of plus or minus 2 millimeters. I'm not concerned when I see little spikes like that that are repeatable because they eliminate each other. The bias is eliminated in each case. Moving on to automated measurement, which is, I think, the trend for the industry, and especially with the TARPs and other things that we have to do for more real-time monitoring. The way to go is certainly to automate inclinometer measurements. So that can be done with in-place inclinometers. And an in-place inclinometer is a string of inclinometer sensors. You see here a few models from different manufacturers that are assembled together that have segment lengths that can be 0.5, 1, 2 or 3 meters long, and here you have more details, and they are inserted into the inclinometer casing. Various ways to do it, either using little tricks like the little table here with a hole in the middle, or a little winch system so that you lower the inclinometer casing, the inclinometer sensors all the way down. 2 minutes. Next one is a string of tilt segments. Our commercial name is a shape array. So it's a bit like the same thing, an in-place inclinometer, but with tilt segments that are pre-assembled on a reel. And then they can be lowered into a borehole. And in that case, because the segments are short, they allow to measure inclinometer profile or cumulative displacement profile that are much larger than what you can measure with in-place inclinometer, just because the segments are shorter. You don't see the scale here, but this is measuring, this is in inches, and it's measuring more than 40 inches of horizontal displacement. All of this can be connected to using data loggers that will be covered in other presentations tomorrow. In order to be displayed automatically in data management software. I have an example here, but since I have only 30 seconds to present it, right, Caius?
45.
45, okay. This one here is an example and that's a situation that you probably face periodically, that the inclinometer casings are deformed too much so that the probe can no more go down the casing, but using a string of steel segments, which are smaller diameter, articulated, you can snake it into the inclinometer casing in order to expand the life of the inclinometer casing and continue the measurement of the displacement profile. So that's what's illustrated on those slides. These type of
natural hazard. So all the way from Italy, welcome to New Delhi. Maybe, yeah.
Okay,
Just kidding.
thank you. Okay. Okay. Sorry. Okay, good afternoon, and thank you, everybody. It's not working. Okay, perfect. I will have today a speech about environmental monitoring for hydrogeological risk prevention. Surprisingly, I won't speak about chemical measurements. I know that in the tailings world, when we speak about environment, many people relate it to chemical measurements, and that was also what came out from the Mentimeter panel that we had before. But the environment is a big topic and is not only related to geochemical measurements. To this extent, I will present other kind of parameters that are really important for the hydrogeological risk related to tailings dams, because other parameter from the environment that is around the tailing dam can influence all the processes and also can act to the failure of the facility. So just a few words about the company where I work. It's LSI Lasten. We are based in Italy, and we design and produce environmental monitoring equipment, starting from sensors and data loggers, software, and so far and so on. We are a laboratory accredited for ISO 17025 for different environmental quantities. And so I will focus on these other topic that is environmental quantities related to the weather, to the environment around the facility. I take some basic definition from the world of natural hazards. So this concept has been described so far many times, but what I want to focus on is that the risk is not only the hazard. So the risk is composed of different parts that are all really important, and so I want to focus on that. So we have the hazard that is in the world of natural hazards is a natural event that has the potential of cause harm. But it's really important to focus also on vulnerability and exposure that are two important parameters that has to be considered. So the vulnerability is the susceptibility of people, property, and infrastructures that are around the facility. While the exposure is related to the presence of people in the vicinity of the dam. So risk is the combination of these three factors. In this presentation, we will focus on the hazard and on the boundary condition related to environment that can cause these processes. So I take this hydrogeological risk definition from, again, the natural hazard world. When we speak about hydrogeological risk, we usually and historically relates to natural events, natural processes that are morphological and are related mainly to landslides and floods. But this concept can be used also for tailings dams and for these processes that lead to failure, and so that has related to this kind of risk. Obviously, how to manage this kind of risk is only a really short description. And really important thing is act before to prevent this kind of risk, and so develop the knowledge. So how develop the knowledge? First of all, having information about the processes. So start from the failure mode, the process, and so define which are the parameters that are really important for the monitoring. So if you want to obtain some really important information and then take some decision, it's really important to define which are the main important parameters. So you can also make some forecasting, and then you can effectively prevent and manage the risk. After, you can mitigate and make some activities, but the important part is obviously the before. So how hydrogeological risk is applied to TSF? So as I told you, it's a term that was invented for natural hazards risk, but obviously can be applied also to tailings dams. So we can define hydrogeological risk with this word. So the interaction between water, geological formation, and in this case also the tailings that can lead to a phenomenon and can lead to harm people and economy and infrastructure. We can list many processes that are related to hydrogeological risk. Now I will only list some of the principal processes, so seepage, leakage, dam failure, flooding, hydraulic conductivity variation, and the stability of the dam itself. Obviously, the changing groundwater flow patterns, and also we can add these other components that are in the world of pollution and environmental risk. So they are acid mine drainage and groundwater contamination. So I want to focus now on the physical parameters related to the environment. So how climate and weather can act to the tailings dam. So today we listened to many presentations that were concentrated more on the geotechnical part and how the processes are inside the dam. But obviously, all these boundary conditions are really important to determine the processes that are inside the dam. So weather can affect both chemically and physically the tailings dams at the micro and micro scale, macro and micro scale. So I want to focus on the macro scale. I don't want to dig inside the micro scale processes, but obviously all the quantities related to weather can really change the processes inside the dam. So the most important variables is rain that can lead to infiltration and many other processes inside. So the increase of the soil water content, the increase of the groundwater level can cause runoff of material and also can lead to overtopping, obviously, when it's really heavy rain, or can also act on chemical processes, so can increase AMD, and also it's one of the most important causes of failure. Then we have many other parameters. So, for example, snow, wind, humidity, temperature cycles, and these parameters are really important for this kind of processes. So, for example, snow and ice, due to the freeze and thaw cycle, can cause soil cracking or obviously increase the groundwater level and water content. Wind can cause erosion and also can blow contaminants around. Temperature and humidity, the most important thing is that when they vary, so they have normally a cycle or variation, so hot and cold cycle or a dry and wet period can influence evaporation and also can modify chemical processes and influence all these AMD or other phenomena inside the dam. And now we have another part that must be faced when approaching designing and maintenance of these kind of facilities, because the climate is not stable, and so far we have big issues with climate change, and climate change affects many topics in the world, but affects also tailings dams, because many of the tailings dams that are already present were designed not considering this variability, and so this uncertainty must be incorporated inside the design of future facilities and also inside the management. In this process, reliable data are really crucial, because there are many models of climate change for the future hundreds of years, but they have really lots of uncertainties. There are really different models, and so it's really important to monitor over time the evolution of these quantities to compare the models and see if the provisions are good. I found this, I think, beautiful sketch on internet. I added some points. It refers about the effects of climate change on TSF. So obviously climate change will provoke changes in normal registered temperature, probably increase, big increase of temperature, and also increase of rare phenomena and the big phenomena, rainfall. So, for example, here is reported that the increase of rainfall can lead to more erosion and also can lead to more pollution in case of accidents, and also the contrary effect, less rain in some periods can lead to less vegetation that can be really a problem related also to dust and wind, and also to the stability of the facility itself. Speaking about big unpredictable events, also wind can increase the pollution around the facility, and also the cycles of hot and cold can damage the facility itself and the stability, provoking some unexpected stresses in the material. How GISTM is addressing the climate change? The GISTM has included requirements for this problem that is more and more important. And in the GISTM, it's included that the variability of the climate change must be taken into account when new facilities are designed. And also is introduced this adaptive management. So as I told you, the models are really different and really with high uncertainties. So it's really important to adapt the management while controlling the data. So it's said that it's really important to continuously monitor and adapt all the management according to this variability of the climate. So going to the quantities, that is the important focus of this presentation. So how we can monitor these environmental quantities, which are the main important quantities related to climate and weather. First of all, we can divide into weather information and hydrometric information that are strictly related. Speaking about weather information, we obviously need to take into account the monitor of the rainfall, both intensity and cumulative one, the snow coverage, the wind speed and direction, air temperature, relative humidity, solar radiation and evaporation are the main important variables for the adaptive management of TSF. Speaking about the hydrometric information, we obviously need to know water levels and groundwater levels, and inflows, outflows, pore water pressure, seepage. So continuously monitoring in an integrated way these quantities make it possible to detect these anomalous situations also connected to climate change at an early stage. And so take this information into modeling, and this way it's possible also to set some thresholds and take preventive measurements. How we can monitor the weather information. I appreciate the mention before about automatic monitor. I think now is the not the only way, but it's for sure something that will be really important in the present and in the future. So with the automatic weather station, you can monitor easily the most important parameter of the climate, and you can select different kinds of models with a sensor of different kinds. The most important thing is that choose instruments with high accuracy and reliable instruments, because it's the important thing is to acquire quality data. And also another point that sometimes is forgotten is that the maintenance of these systems is really mandatory. For example, here you can see an automatic weather station with separate sensors. So here we have a rain gauge for the rainfall, here wind speed, wind direction. This is a sensor for global radiation, temperature and humidity. Here you can see that the station is more articulated, but is with high accuracy sensors. In this case, you can also, for example, choose a more compact solution with all the parameters inside. Here we have 7 parameters, the 7 principal parameters. Obviously, it's more easy to install, but for example, if you need to replace a measurement cell, you need to remove the entire sensor, while in this case you have different sensors. So you have pros and cons in a standard or compact solution. The really important thing, as for all the other kind of monitoring, is the data management. So data must lead to decisions. So it's really important to take all the data together as a comprehensive system, and also to design the data management that must be taken into account from the early beginning. So just few words about data management that was already mentioned in the first part. So it's really important to collect, process, and maintain the data organized in an information system. So because you need to have all the tools to make the right decision. Few points really fast. So it's really important to collect the data in the right way. So it's really important the quality, the automation, and the spatial and temporal consistency of the data. So starting from the field, then it's really important to store the data properly. So the data must come in a unique site, a centralized site with integration also of different data. You can decide if you want to store the data locally or on cloud. And also you need the backup and redundancy. And also it's really important to rely on standards on data with formats and metadata that are really important. Data integration is really an important thing nowadays because we have a lot of data, and it's really important that they can be integrated together. And also data quality after the database is set. So you need to search for error, validate and calibrate all your data. It's really important for people that are in the mine, that are on operation or on design, the accessibility of the data. They can be accessible really in a user-friendly manner. And also in this way, it's possible to make some analysis in a good way. And also really important these days, data security, so cybersecurity and privacy, and compliance, and obviously all these data management must be designed properly. So in conclusion, we spoke about hydrogeological risk in the TSF related mainly to different processes that are strictly connected to the weather and to the external variables, not only inside the dam body. And so the management of environmental quantities is really important nowadays with the climate change. So it's really important to adaptively manage the facility as the GISTM suggested. So if you continuously monitor the environmental parameter in an automated way, you can follow over time the evolution of these processes and take the right decision. And take note that data management is really important. That is a proper project that must be conducted from the beginning to the end of the life of the facility. Thank you.
Thank you very much, Greta. So we're gonna go to Sam Johansson online. Hi, Sam, can you hear us?
I can hear you fine. Hope you can hear me also.
Yeah, very well, very well. So
okay, really good.
Just a few words about Sam, principal and CEO of Hydro Research. Maybe Sam, I'll let you introduce yourself briefly for a few minutes about yourself and your career. So I'll pass it on to you.
Yeah. Okay, then I will try to share here my first slide. Seems that like you can see that. Good. Yes, I'm Sam Johansson, and I've been working with fiber optics for about 30 years, and that's what I will tell you a little bit about today here. I have also been a proud member of the ICOL monitoring committee for 20 years, but this year I'm a former member only. So I have been listening to the meeting here, and I think you have a nice time, and I really enjoy listening it, but also enjoy to be here by this way here. So here we will start, and I will tell you about the distributed fiber and how we have applied that in tailing dams. And I will try to share experience that we have gained during this time, and I will not go into details about the monitoring system and how it's work, but I will tell you some steps from monitoring to evaluation, and with the example from applications, and hopefully you will learn a little bit about the potential and limitations using optical fibers. I have taken results from real cases. Unfortunately, we are not allowed to present everything that we are doing, but what I present here is okay to share. We have learned a lot, and I will also try to give you some conclusions here in the end. Next slide here. This is the background. We started here in 1998 with installing fibers in dams, and that was a hydropower dam that was built up. So that was part of a new dam. And you can see that during the early 2000, we had a lot of installation coming out in Sweden. And today we have about almost 100 dams, more than 100 dams in both for hydropower and tailing dams. And most are in Sweden, but also in Canada, Norway, and the US and Finland. We have some sites here. And you can see that it's a very long length of cable installed here, about 160 kilometers in total, and that's what I will tell you a little bit about here. If we go to the tailing dams, we have 8 system runnings, 8 installations worldwide and 6 in Sweden. And some of the units are taking care of several dams, so there are more there. And we have 9 permanent monitoring systems. So you can say that this system has been proved a lot, both in Sweden and in other countries here. And each installation is, of course, an individual. If you look at the installation up in the northern Sweden, in Kiruna, where LKAB has used this a very lot, we have over 40 kilometers there, and it's increasing each year. And also this year we had some cable installed there. In the other, they are smaller, 7 kilometers here in Malberget and Aitik and so on. And we have 1 installation going on. So this is a natural way of using this technology in Sweden, and it is accepted of all the major mine companies in Sweden. And you can perhaps ask, why do we have so many here in Sweden? And I think the most important thing is that we have seen a willingness to support this new technology when it came in the early 2000s. And the second point is that we have found that this distributed information, I will tell you a little bit more about that later, gives a very valuable information, and that can cover the entire length of the dam. So this is a good complement to point sensing like pressure sensors or seepage monitoring system, which collect data over a larger distance. So to get very detailed information all along the dam has been found very, very useful. And We have also seen that cables can be installed, of course, in new dams where we can put them directly during construction, which is good, but we can also install the cables in existing dams. That limits, of course, the application and the accuracy, but it is possible to think about that. And the good thing with the fiber is that you can measure several parameters also. You just change to another readout unit, and then you can measure something else. We have, during this time, developed a lot of the evaluation process, so we can do it online and with remote operation. And these cables has been proved to be very durable. We can measure better today than we could in '98 when we started here. The sensor is the cable and it's the same, but the readout unit is much more better today than 30 years ago. And the units have been found very reliable. They have, of course, a lifetime. It's like a computer. So we are expecting about 10 years lifetime for these units. But it's very easy to replace them and do the calibration. And the calibration is another feature which is very useful here for this system, because we can calibrate the entire cable length within 10 minutes. So calibrating 10,000 sensors in 10 minutes, that's pretty good. And we all know that calibration is very, very important. So today we have 4 different technologies that we can use in the same cable. The first one was the temperature measurements that started in 1997. And then we started with strain sensing. Strain is always along the direction of the cable, and that can be measured. In 2015, we were asked to build a system for dam breach verification. And in 2017, we started with distributed acoustic sensing, which is using the cable like a long line of geophones. So this is the technologies that can be done in these cables that we are installing. So if we then start at the fiber break, which is the easiest one, then we look at the signal losses that is occurring along the dam, and look at this very accurate. And this system just say yes or no that the cable is intact. So if the cable is broken, then it will react here and send an alarm. So that's the easiest one. If we look at the temperature, we are measuring that in order to detect seepage flow changes, and also if we're measuring long term, we are looking at the seasonal variation, and from that we can calculate the seepage flow rate. And this is done, so to say, along each meter or 25 centimeter all along the dam. So that's the idea with this one. And we are working together with the Silixa, or Luna as they are named now after they was bought up. So that's example of the units that we have installed. They have also a good system for strain measurements, and you can see the strain resolution here is 1 microstrain. So it's about 1 micrometer, you can say here, because we have a sampling resolution about 1 meter. So very accurate system. And then we have the acoustic system. All boxes looks a little bit similar, but the inside is not the same. And then you can use the fiber as a geophone or a hydrophone or whatever. And the idea with this is to detect velocity changes in the soils. So we're using the classical seismic approach, and but we are measuring it by the fiber, and using that we can see changes in the volume. This is which is apart from the cable, so we don't we can see a little bit further away compared with the temperature and strain, which is exactly what we're measuring around the vicinity of the fiber. So here I show you where we can install them, and this is the typical in a new dam. We can put fibers here in the upstream filter, on the crest, downstream filter, and in the horizontal filter, and in the dam toe. And the typical installation in the hydropower dam is to have it on the crest, in the downstream part here of the central core, and in the dam toe, and that's the most common thing. Some cases we have drilled and installed the fiber in vertical standpipes. So this is how we're doing it in hydropower dams. Here I'm showing one example in a tailing storage facility. This is also an example how the temperature can be used for seepage detection, assuming that we have some water seepage coming this way. We can then, by measuring, having a cable here, we will have a response of the temperature during the year, which is pretty large here. If we go a little bit further downstream, we will have a smaller variation, and so on. We know that the temperature pulse, that is an effect of the seepage flow, is attenuation with length. And if we have it here on the crest, crest of the starter dam, we will only have a small variation because here we have a distance from the water. Here is one example of a dam in Norway, where we put a cable on the crest just to be able to verify a dam breach. And in Norway, they have different systems. So this is one of 3 systems that they are using in this dam. And it was very successful, and today they have it in 6 dams. And we have developed the system a little bit, and we have 2 units running also in Australia. So this is this easy way of telling yes or no. We have no idea where the cable is broken, or no answer in early warning. Before something happened, we will just see that something has happened. However, the good thing with this is that we can measure very with high frequency. We're talking about less than 10 seconds or something like that. So it's a good ongoing system. With the temperature, as I mentioned, this is the seasonal variation that we're looking at. And the seasonal variation that is measured depends on the inflow temperature of the seepage water. And this is one example with a model where we have a small leakage through the core. And you can see here how the warm temperature from summer are going in here, and it's attenuating, and then you have the winter temperature coming here. And if we then look at the variation here, we can see that just downstream we have this blue curve. We have this a little bit lower than the other one, and that depends on that here we have a impact from the heat conduction from the air, from the surface. So therefore it's much better to install the fibers close to the downstream part where we have a longer distance to the surface. So installation in new dams is optimum. Then we can find the best location where to put the fiber and just measure what we are looking for. This is one example, and here you have the temperature along the dam between change 390 to 450. So it's 60 meter. And here is, you can see temperature curves along temperature profiles at different dates. And you can see that in this area we have small temperature variation during the year, but in this area we have larger. And you can also see that here in the spring we had cold temperature, but you can see during June here already it's going up pretty quick, especially here in this region. So this is a sign that we have seepage entering into the downstream toe. So then we can keep track of it, and we can see if we will have changes, if we will have an extension of this leakage, or if we will have so to say a higher temperature. Then it's also a sign of increased seepage. This result can also be plotted along the dam here, and you have the time here, and this so-called water flow curve, waterfall plot shows, so to say, areas where we have larger temperature variation and smaller. And this is a very good picture of looking at how quick you will have this reaction all along the dam. Of course, you can plot the temperature along the line. In this case, we have two lines in the downstream part, just one below the core of the dam, and this is in dam toe. And the idea is that we can distinguish between flow that passes only through the dam and water that passes in the foundation coming up in the drainage toe. And here is how we can calculate the seepage flow rate with time. And there you can choose how long distance you will cover. This is another way we can make alarm. We can estimate from the seasonal variation what the next data will be, and we can then calculate the deviation. And the deviation is plotted here, and you can see that we have very small deviation, these blue areas, but at some times you will have larger deviation, and in some case it depends only on the snow melt that goes here or rain. So we can see if it's raining or snow melt going on that can affect the drainage. But if we will have an increased seepage flow rate, we could detect that also here. This is
Sam?
Yes. Yeah.
Just maybe a couple of minutes left, if you don't mind.
Yes, I have speaking in 17 minutes here, so I will take it within 20 here. Be sure. Okay. This is the strain movements, and this is what we did here in the research project, which I can publish. That I can't publish, but we can see that in some areas like here, you will have small changes. The system that we are using now is much more accurate, and you can see that the difference between different measurements are very similar here. You can also see that we can measure both extension and compression, and these measurements are taken from the test at the experimental dam that we have had here in Sweden. Some words about distributed acoustic sensing. We have used that in a couple of dams and also in this experimental dam. And we have learned a lot, and we think it's a good idea. It needs a little bit more development to see, but it may be useful within the next 5 years or so. And from that we have also done some acoustic modeling and try to understand the potential with the method. So how to conclude here? I think you should always consider to install optical fibers. That's you can use them already today, but even in the future you can use them because their application will be better and better. And consider that you will be able to cover the entire dam with distributed sensing. And with the temperature, we can detect minor seepage flow changes in space and time. Automated evaluation and alarm will work. Strange sensing, we can detect where movements have occurred, and if you're also measuring online, you can also see exactly when, and you will have a very sensitive system. DBV, the dam breach verification, high frequent monitoring, but just either yes or no. We are working for some improvement here, but as dam engineer, we are preferring to have systems that give you some kind of early warning. And acoustic sensing combined with ambient noise is now under development, and I think it can be applied in the future and have a potential also there. So that was it. Thank you very much for listening.
Thank you, Sam. I invite you to stay on the line, and I want to invite all the speakers to come here for a Q&A session, please. Yeah. In the audience, please prepare your question. Have a seat. Have a seat. Have a seat. We have microphones on the table. So let's get going with the questions. Please raise your hand and ask the question to any of the panelists, please. Yes, please.
Yeah, I have a question from Sam itself. So the optical fiber system we have seen, that is fantastic, we can see. But just wanted to know what is the life of this optical fiber?
The lifetime is expected to be around 50, 60, 70 years. So we have learned that if the cable installed in a good way, it will last very long. In our case, the oldest was from 1998, and it's working perfectly now. So that we do, but I think it will last for, as I said, 50, 60, 70. That's what they're telling us from the telecom area.
Thank you. Yes, at the back.
Utilized for the masonry dams? The optical fiber cables, can they be utilized for the masonry dams?
Masonry?
Yeah, masonry or concrete dams.
Masonry or concrete dams, Sam? I think the answer is yes, but you can complement that.
Yeah, I mean, it's the important thing is what will you gain with temperature movements, for example. I mean that you can measure with the optical fibers, but for example, if you will measure movements, you have to add the cable on the concrete, and that's not so easy to glue that very strict. It is possible, but it's maybe not the best way. So think about how to solve the problem and how to measure the thing in the best way. I mean, fiber optics is good in many ways, but if you have more point information, then I think you should think about something else, because the unit is not cheap itself, but okay, you can measure tenths of kilometers with one unit and a lot of sensing points. So I know that it has been used for temperature measurement during grouting in concrete dams, for example. So that's one way. And of course you can measure seepage flow in the abutments of a masonry dam or concrete dams or in the foundation.
And I can just complement. familiar with a project in Northern Europe where they used fiber optic cable to monitor strain in a bridge. So they install it in the bridge, and they will actually monitoring deflections, summer versus winter, and so on and so forth. So definitely it's applicable in structural engineering. There's no question about it. But it's a matter of making sure what do you want to measure, and obviously in your situation, strain would be quite important for you. So we have a question. Yes.
You showed for optical fiber installation for the new dams. How we are going to install for the old dams in which geosynthetic fibers is installed in the embankment area and the slope to prevent the water contamination. So how we are going to install this optical fiber in the embankment or slope area? Since IPI, it is very difficult to install IPI inclusionometer because there is chance of the breach of the geosynthetic fiber in the embankment area.
It was a little bit difficult to get all information here, but yeah, want to comment, David?
A repeat and a comment is basically installation in existing dams. That was the question. And from my experience, I installed fiber optic in existing dams. I would install them in trenches, and you would install in the crest, and you would install them on the downstream face. And you build those trenches. I've had trenches of 1.2 meters with proper sand placement, proper placement of the cable, and you can still get value out of it. But if anything else, Sam, that you want to add?
No, I think you're right. If you put them on the crest, you can use them for strain measurements and acoustic measurements. You will not be able to measure seepage on the crest, hopefully. But you can also put them in the just downstream. If you if you have a drainage system there already that are taking care of the water, then you must try to get the cable upstream that. But if you have nothing, you can put it in the special trench just downstream. If you're there to make a trench there, I hope you have saved them that you can do that. But you have to think about that. That's the way in existing dams.
One more question to the team from Hexagon. You was describing the surface monitoring equipment. Can it also predict the underlying reason?
Sorry?
Underlying reason for the any displacement or something?
Whichever is visible, it can be done. If it's not visible, it can't be done.
I'm asking for underlying reason. What is the reason for this displacement or something abnormal in the prediction which we are getting from the surface monitoring equipment?
Sorry, I'm not getting you.
What is the cause of the reason? What is the reason or cause for the any displacement or something abnormal erosion or something?
It can be a civil reason. It can be a when at the time of building must be some displacement, must be some low cost material, something has been done. It can be a reason, but not sure what can be a reason. It can be anything.
Yeah, you can. I mean, depending on the location, you can get a frost action. You can get movement. You can get foundation movement. So you can get many reasons for cracking and superficial cracking. So yeah. Any questions, please? Here. Oh, sorry. Yeah. Yes. But yeah.
If you have any existing dams.
Yeah, installation in existing dams is in Sweden for tailings dams often done when you put the buttress.
Okay. Yeah. Yeah. Okay. So let's go there, please. We had a question there first, if you don't mind. Edgar, you're running it.
Please, I need us to know how to obtain the calibration certificate. If the company or has installed PWP piezometer before, but now it's not possible to see the real measurements on site when we take measure.
So you're saying you don't have the calibration?
No, no.
Do you know the serial number of the instrument?
Yes,
If you have that, you can contact the manufacturer and they have record, so we can send, I know I can, yeah, I'm sure you can as well. We can send you record if you have the serial number.
Just a question just to be the same speaker. Just wondering if you run into a situation where you have to install the pushing isometers horizontally, and what is the practicality of it if you run into those kind of situations?
I suppose it can be done. I personally have never done it horizontally, but you just have to, you'd have to apply enough pressure to push a ladder, but you still would have to treat it the same way, monitor the pressure as you're pushing it. So it might be a challenge setting up the rig, trying to push that way.
And usually when you install a pushing disarm, either you push it from the surface, but up to 30 meters, depending on the stiffness of the soil. Beyond that, it's more difficult. And then you have to do a pilot hole. You push the pushing pistol at the bottom, and then you grout or you seal above the pushing pistol. So in your case, horizontal, yes, you have to set up the drill rig for that. I guess that would be feasible, but the sealing of the hole will be more difficult. So you have to find a strategy to how to seal the hole. Otherwise, you're not monitoring what you think should be fine. Maybe a small, maybe a reality solution would be a small inclination of 10 degrees, and then you'll be able to pump right in there and seal. Yeah, maybe the solution is that.
Yeah. Any other questions? Yes, a comment? Hello? Yeah, please, a question, yeah. Yeah, please.
I've got one for each one of them. Well, first of all, just tell Sam that it's great to see him on the screen, and that we're gonna miss him a lot at the TCQ meeting, because Sam has been part of our committee since ever. So that's for Sam, and so looking forward to seeing you soon, Sam.
Come on, he's a young fellow. Look at him.
And then I've got four comments and questions because I think installation of fiber optics in existing dams, yeah, absolutely can be done. So for Greta, it would be, when do you recommend, if you could insist on when to start monitoring all the environmental variables, which are very important? So that's for you. For Pierre, it would be if he could share. Pierre has an excellent paper from last year and another one before about grouting, fully grouted piezometers, and the details about the grouting mixes depending on the permeability of the medium. So I think he could maybe elaborate on that with Matt, and if he could share that paper and we could include it with the presentations, I think that would be great for everybody. So that really has to do also with the nested arrays of piezometers, especially when we have a downward flow. If we only use one piezometer and one vertical drill, we may not really capture the real position of the phreatic surface. Yep. So having at least two, but even 3, 4 piezometers in the same vertical or very close to each other. But nowadays we can have one cable and several piezometers with just one cable, which is great. So that goes for them. And for Vijay, I would say if you could just tell us a little bit about the accuracy of the measurements based on the distance. how far, I'm thinking of the total station, the robotic ones, and about the pillars, like being in sound rock and the distance. So the maximum distance we should be measuring from. So that's for you. And then for Matt is really about the zero readings, and if you could just make some additional comments on the environment, the corrosion when we have a very aggressive or abrasive environment, and about the importance of measurements and noting everything down and all the details during the drilling. So that's for each one of them. Thank you.
Yeah, so that's 4 questions. You need to buy beer in order to get all the answers. Okay. Okay, Greta.
Okay, thank you for the question. Speaking about when the environmental monitoring should start, I think that it's really important to have all this historical information also for example, for starting from the design of the facility. So if you don't have a station in place and try to figure out how to gather historical data, probably from the country itself, some environmental department, and starting from that, then install your own station to have site-specific environmental quantities over time.
I think you was more specific. How many years before you actually start the construction you would suggest?
I think that all the data that you can obtain in the past, because you know that the return time of the rainfall or any other natural phenomena.
What have you seen? 3 years, 5 years?
More.
No. When do you install it?
Okay.
When do you install it physically? The weather station at the site?
After?
No.
Sorry,
Before the project.
Okay. You can gather other historical information not from your own station, but then when you have in mind to develop a facility, to project a facility as soon as possible, obtain this data.
I think if I may comment on my experience with environmental assessments, it's quite typical 5 to 7 years to have actually weather stations on site physically. Yeah.
Okay, thank you.
Yeah. Thank you, Greta.
Yeah, Manuel is asking me to share a piece of work that we've been doing together with the US Society for Dams on the grouted piezometers. Actually, I will be talking a little bit about that tomorrow in the presentation that I will have on the it's called What Can Go Wrong During Installation. So I'll address that. And yes, I will include that paper.
Okay. So you have the magic potion for the grout?
The soup recipe.
Thank you. Okay.
Thanks for the question. And if I talk about the robotic one, we have 2 different modules, which is called 0.5 second and 1 second. If I go with 0